Alright. A few minutes past 7. We're about to do some electricity and magnetism. Do a little survey and see which one of them was the hardest topics for people. And this turned out to be one of the most requested. So we'll start off with this. Welcome Shimor, Kievan, Akash, Nyasha, Boone, Anika, Aliyah, Nathan. Alright, so we're just waiting for some people to jump in. Touchdown, Gunplay. I probably shouldn't be saying your name. Josiah. Merry Christmas. Mark, Makila. Hi, Makila. Dariel, Ting, Pablo, Nikolai, Noah, Chrissy, Gabriel, Run It. I was second though. It was good. So POB was good. I hear everything running smooth now. It was just the hard exams was just maths, English B. That one other one. POA, maths and English B. Everything else run according to plan for us. Alright, and so the hairline going back slowly but surely. Yes. I was taking a look at it in the mirror. You kinda getting a little kinda something coming in. Yes, sir. I want to shout out. Joey, hold on that shout out, my brother. Blessings. How much people we have inside? We have 135 people inside already. So y'all, right now the live now warming up, so you can feel free to snap. In fact, everybody here, listen to me. We gotta get this live pumping to the max. What's happening with Caribbean people is when I do a live the night before the exam, everybody there. Everybody and their grandmother and their auntie there. But like if I do a live not before the exam, the night before the exam, people will say, we have time, man. We have time. But physics is a scene. So I want everybody just take a snap. If you're on Instagram, take a snap, post it on your story and let people know we're doing a little physics course here in electricity and magnetism. And physics and maths are my mains. Those are my main soldiers. This is the book I learned CSEC Physics in. You can even see the front cover, the condition of the book. The condition of the book, boy. This book have maybe about 20 years. You just see the back of the book. But I have a new one. To it. This is the physics for you. Now this book is not according to the CSEC syllabus. But this book is what I can't show you the contents of the book, but this book is what really breaks down physics for me. Like when I got this book in Form 1, before I reached the school in September, I knew everything in this book because the book's so friendly to read. So physics was never, ever a problem for me. The other physics books, we have other physics books. I have this. I have a good bit of other physics books. So you know, I just rail by books, textbooks. Let's have a new one here from a lesson teacher who teach me lessons in Cape. This is one of the latest on the market. I like this book because it has everything. This is by Manny. Anybody is take lessons by Manny? Samlal Manny, a teacher in CAPS. Good physics teacher, really good physics teacher. I like all the I like the book. It just have a few problems I have with the book. You know, I don't really recommend textbook. I buy a textbook. The only textbook I really recommend is the Antindale by the chemistry person. If anybody want me to recommend the textbook, they gotta pass some cash and the textbook better be good too. I wouldn't recommend it if it ain't good. Alright, so yes, sir, IT. Yeah. What about IT? IT, you wanna touch down on some IT too? IT requirement to do. I was reading some IT today, but wow, all the real definitions to learn, boy, and real acronyms and things. Jeez, I need shiz. Next, somebody say next. No, we waiting a little while. We starting up in 2 minutes. We just taking a little talk here. We take a little 5-minute talk, especially when we're on the last day before exam. Integrated science is coming. Physics is coming. Theater arts is not coming. What is that? So we're doing electricity and magnetism. That will cover circuits. IT going to be stressful. I want to try and see how much I can do in IT. Last year I wanted to do IT, I didn't get to do it. If I could at least do maybe some programming or something in IT, that would be good. But the requirement to go and do some revision because I didn't teach IT in a while. Alright, so chem was easy. Yeah, chem was easy. A whole start of things was easy. So yeah, How many likes on the video? Like, give me a little like count there. How much likes we have on the video? We're about to start in a little bit. How much likes we have on the video? Make sure and press like. I want this video to get as many views, as reach as many people as possible. Alright. If you haven't pressed like, press like. Let the algorithm in YouTube do what it do. So do algorithms in IT. Yeah, programming would be very nice. I have paper ones. Shut up about maths. Please do integrated science. What's that? Yeah, use my cat. Algorithm is the biggest challenge in IT. Acceleration, calculations, physics gonna come hard. We don't know. Look like these things coming easy for now. So everybody take the screenshot and post on Instagram already. Now we're going to mash up some physics now. What name this boy? Securing the bag. We're going to secure the bag where physics is concerned. We're about to go down. Everybody press like. We're only 105 likes. Half of the amount of views. We'll try and bring it up to get closer. So we're doing electricity and magnetism. Maybe we'll do waves afterwards. So let's but I want to do as much physics as possible. Maybe if I could cover all of the hard stuff and a little bit of the easy stuff too. Alright, let's see if this is working. Are you working? This is the syllabus here. Let's put it back better. If you're hearing crying and thinking in the background, you know how things is going. So this is the syllabus here. So tonight we're gonna lock off. What you're seeing is 1, 2, 3, 4, 5 sections, right? Tonight we're gonna lock off 1/5. We want to lock it down. We want to secure the bag. We want to completely lock this down. Completely, right? Maybe tonight if we finish early, maybe we could try and completely lock this down too. But that's a maybe. I gotta take it easier now. I reintroduced my body to some sleep yesterday. After them series of long lives. Ooh, that chem life was a scene, but wait. I think we over prepare for chem.
In the hospital.
You went to the hospital? I don't think so. Yeah. So these are the topics. These are the topics in electricity and magnetism. Electrostatics, which I already did a video on, all of electrostatics, but I'll talk about it tonight. Current electricity. Electrical quantities, power, equality, E, the formula E, circuits and components. Knowing your circuits, knowing how to do your little circuit diagram and everything, right? Then electronics, magnetism, electromagnetism. When you post on Instagram, make sure and tag me in the post as well, at Kerwin Springer. So if you're not following me on Instagram here, I don't know how you're doing it yourself, at Kerwin Springer. Especially if you plan on doing stuff in A-levels, I'll be continuing, A-levels, CAPE, I'll be continuing with CAPE, right? The CAPE students. Alright, so free up yourself, brother man, free up yourself. Alright, so let me get started. Any questions before we start? Let's get this bread. Everything need to do here. You want some? Who wants a Jamaican boyfriend? Over prepare until you not even near slide. A single definition. IG doesn't allow me to follow anyone else. You over follow people. That possible. Free up yourself. Thing. Back boom. Alright, so let me get this so I can follow along. Exactly what you all need to know and not give all you too much extra stuff. Now, the technique for revising chem was the concise book. The technique for revising physics, I always say to revise physics, you want to try and understand as much as possible. You understand what I'm saying? You understand what I'm saying? You can't really revise physics concisely and just pull out the points and think, nah, that wouldn't work. It will be hard for you if you do that. Physics becomes very easy for you when you actually understand what you're doing, right? So we're starting off with charge. We're starting off with electrostatics. I hope my pen works tonight. So electrostatics. I'll be asking you all questions. Let me get my next textbook too. I have it in point form. So I'll be on precision. Yeah. How you all feel about electrostatics? That is just like a little beta question they could ask in the beginning. The big formula you need to know in electrostatics is Q equal IT. Q equal IT. What Q stands for? What does Q stand for? What does I stand for? What does T stand for? So this is the first thing you'll get. So enough blind and get straight to it. We in it. We inside. We inside. What does Q stand for? Well, you should know Q stands for charge, right? Charge. Charge. I stands for current, right? And T is time, obviously. And the units would be in seconds, current, amperes. Anybody put some units? Q is in coulombs, right? Coulombs. Alright, so that's our SI unit there. Fun, you're doing the most right now. Try not to do the most. You need to know what, like the friction, when you do the friction experiment, some things will be negative, some things will be positive. What I'm talking about is like if you have a rod and you rub it with cloth, remember some of the electrons is come off, one is being negative. Sometimes when you rub it with cloth, the electrons go in. Well, here's the positive ones. The ones that turn positive. Where's the one that turn positive and where's the ones that turn negative? What are the ones that turn positive? What are the ones that turn negative? I'm an asking if I do office administration. But I don't have a office administration. I don't know. So the rods. Yeah, which rod? Nobody in seen it. Okay, well I'll give you a clue. The one that turn negative, there is the polythene. You all remember that? Polythene rod experiment and you rub it with a cloth. The ones that turn positive would be like what is the cellulose acetate? Cellulose acetate. Oh, and glass as well, yeah, glass. Let's try to make sure I'm pen writing. Certain parts of my screen, you know, too good. Come son here, I don't kind of screen cleaner here. Yeah, glass. So some people never see this. We didn't learn this. Well, yeah, now you know, but normally they will tell you which one it is. But we covering everything in it. Only don't worry. We covering everything. Glass and next one that turn positive is some ebonite or some kind of thing. So, but I don't think I ever see that before. Right? This is like if you have the rod, a rod, and I do a video on electrostatics. You can probably take a peek at that when this live done. You have a rod, depending on what the material is in your material, the rod made out of perspex would be positive. What material? You rub it with some kind of cloth. Now, the ones that are rubbing to turn negative is how to rub it with a cotton cloth. No, full cotton, I think. And this one that are rubbing to turn positive, they normally use silk. Oh, not too important, fur, wool, them kind of thing. This one you use silk. Right? Not too important. What you catch the idea. But you need to explain what happens. And I did that in the video. When you're rubbing it, electrons actually transfer because electrons can move. So electrons on the surface would either go this way, or in the case where it turns negative, electrons from the cloth actually went that way. So it's obvious now if you're turning, if the rod gets more negative, it's because it get free little electrons on the surface. It get a surplus of electrons. If the rod get positive, it's because it lost electrons. Alright, so we'll reach generators and thing. We just treading along. It's a full course revision. Everybody should know how an atom look. I'm skipping that. I should mention this. Charge is also equal to the number of electrons times the charge multiplied by the charge on one electron. Right? Anybody ever see this formula before? If you ever see, why is in the chat if you ever see this? I must I must skip atom. I mean, if you don't know what atom is, what going on? What going on with you? Right? That's why I say it's important. Don't take all the little basics. Don't skip the basics and wait for the hard stuff alone. Take in the basics. So you have your neutrons, you have your protons, thing, the electrons on the outside. We don't need to talk about that. If you ain't know about that, go and study. Better you start back from one. Right? So you must know your protons, your neutrons, and your electrons. This is just a formula that's saying the net charge here would be equal to the number of electrons. Like if they give you a question now, we'll see. And multiply by the charge on one electron, which is a given. The charge on one electron, anybody know it offhand? It's 1.6 times, it's very small, 10 to the minus 19 coulombs. It's a negative charge, so I could put negative in front here. That's the charge on one electron. So one electron has a very small charge. My pen and writing too hot. One electron has a very small charge. That's the charge on one electron. So if I want the total charge, I need to multiply the number of electrons by the total charge, right? So for everybody who's saying, why is this? This is just a simple little thing. A simple little thing, trust me. And you might, if it come, you might be just glad I mentioned it. It's just a simple little thing they might guide you if they try to bring something like this. There's a you'll more see this in keep, right? What would happen? What would happen if I have an experiment and I have two types of rods? I'm gonna make this a different color. And I have two types of rods, and one rod is positively. So where's the positive one? One rod is negative. So this would be like the acetate, the cellulose rod. And this would be like the polarity rod. Right? Nothing. You just wait to write. That's all. Polarity rod. I'm going to start zooming in and out to write. They would attract, right? So there would be some attraction between here. Now I should put the arrows like this. There would be some attraction. There would be some attraction there. And obviously, if it was two of the same rods, they would repel, right? If it was two of the same rods, they would repel. Now, can anybody write out the law of conservation of charge? Anybody know the law for the conservation of charge? Anybody know the law for the conservation of charge? Nope. What? Energy? That probably not. Energy cannot be conserved. That's the law of conservation of energy. So people gave me the law of conservation of energy. But the law of conservation of charge, yeah, Antonio, I see you comment there, bless up, but physics is not tomorrow though. Physics is Monday. So that's why we're starting now. Okay. Net amount. Right, so Aliyah has it there. Luby the bread van passing, girl. If you want bread. Net amount of electric charge net amount of electric charge. That's now, with this, can you do some NT something? Y'all, NT coming soon, NT coming soon. If y'all are watching the stream, who just messaged me there, NT coming soon. So the net amount of electric charge produced in any process is equal to 0. So I'm going nice and steady here. Net amount of electric charge produced in any process is equal to 0. So that's the law of conservation of charge. A lot of people didn't know it. Now you know it, right? So if you have a process and electric charge is being produced, the net amount of charge going from left to right, moving about it, going to end up to be 0. It just balances off. Right? So charge is conserved. Now you can charge something. You can charge up something by either conduction or induction. Everybody here can explain induction, explain conduction? Can everybody let me see some whys in the chat. Whys in the chat if you can explain conduction and induction. Cohen Springer, please write a little better. Only when I have my new iPad, my writing will be stunting, eh? But right now, conduction versus induction. That's the best I could do. How is that? No, we can't explain conduction and induction. Well, two ways to basically charge up something. You can bring the positive rod and like touch whatever you want to charge up, and all the electrons will run into it as it conducting it. Conducting has to do with conduction, yeah, but we're talking about in terms of charge. We're not talking about in terms of heat. Remember, we are in electricity and magnetism here, so don't tell me about heat. Induction is when you put a charge up. Yes. Induction happens when you put any charge object next to a neutral object or something, and it induces the charge without touching, right? Induction means without touching. Right, I just reading through some answers. One is not like frictional or something, so where induction is the neutral object. Yeah. Conduction is the transport of charge, yeah. Induction is when the charge is shared through electromagnetic field from one rod to another. That's nice. Bajan King gaming. We onto something there. Right, so the conduction has to do with, well, it's touched. So you have to remember the word touching. Some touching is happening here. And if I put you in the center of the screen, if you write better. So we actually have touching happening here. This means like if you have a charge rod, like you said, your rod was negative, and you bring it next to any kind of conductor. Even if this conductor is neutral, electrons are going to be like whee and run off into the object until it's balanced, until there's a balance. Now remember, the charge is conserved, right? That's conduction. Now induction is a little more tricky to explain. Induction happens due to the electromagnetic field, right? Let's say we have, and I explained this very clearly in the video that I did. Before. Let's say we have a net amount of negative charge here. So that is like a polythene again. And we bring that next to a neutral object. Let's make the neutral object a rectangle. what happens is all this negative charge here, if we have some negative charges in here, this has to be a conductor. We have some negative charges here, right? A lot. Extra, extra. This just extra. This negatively charged. All this negativity here is going to cause repulsion of the electrons here. So all of a sudden, these electrons don't want to be on the edge here anymore. It just had too much electrons on the side. Like charges repel. So all these electrons are going to try and pack down here. What will that do? That would make this, that would expose the nucleus there. That expose the protons. So there will be a net negative charge here and a net positive charge here. And now remember, this is still negative. This is still negative. So if this is still negative and all the negative charges ran away, exposing positive charges here, there's going to be attraction. And that's the whole process of induction and what happens during induction. Let me see some Y's in the chat if you understand conduction and induction there. Y's in the chat, good. Good. Alright, great. Now, if this is too small, induction will be hard to occur. Induction occurs best when the object is grounded. This will allow the electrons to have space to run away, because remember, when they see plenty electrons here, they want to run away. But if this is small, it didn't really have nowhere to run. But if it was grounded, it would run through the ground. And this is the principle of the lightning rod, right? Thanks, check your IGBM, right? In a timing. So this brings us to talk about electric fields. Now we have to talk about magnetic fields sooner or later, but we'll talk about electric fields first. So there's some diagrams to draw. There's the diagram if you have a positive charge, then there's the diagram if you have a negative charge. Now these are point charges. Let me just draw it back a little better. Positive, negative. And you draw a little circle around it. It's a point charge. Everybody know how to draw this diagram? Why is in the chat if you know how to draw this diagram? Excuse me. Yes. So the positive just now, let me just verify this. So everybody know how to draw the diagram? We're going to talk about that just now. The positive charge, both of them look like this. And I would draw it like 1, 2, 3, 4, 5, 6, 7, 8. You know, top, and it has to do in between. This one will look like this as well. But the direction of the arrows is the key here. If it's a negative charge, we have the electric field going like this. If it's a positive charge, we have the electric field going like this, away from the positive charge. That's simple, right? Now, if we have a positive charge and a negative charge close to each other, you need to know what happens. The forehead shining, you move towards the move outwards from the thing, right? What would happen here now? Well, draw little circles around. I would draw one straight like this, then the bend, then maybe one like this, one like this. That's what we expect, right? You're getting that flow. Everybody catch the idea of this? Quick memorization. All you need to know is going. from the positive into the negative. Very good, very good. Now, the last thing you need to know, oh, if you have a positive and a positive, what will happen? You're going to get this taking place, right? Kind of don't touch me situation taking place here. So it's running away from the positive, but it can't go into that other positive there, so you have that taking place. I draw that diagram kind of bad. And the last but not least is if you have plates. So the plates is as simple. If you have positive and negative, positive, sometimes they'll do it like that. Everybody get taught this, right? Everybody get taught this. You draw all in the center, straight, and the ones on the end, you curl it a little bit. Once again, positive to negative. And that's about it for electrostatics. Make sure you know all these diagrams because they come a lot. They come a lot, as simple and ridiculously simple they are. They come a lot. The conduction, talking point, make sure you can explain it. They come a lot. I never see this. Laws of conservation of charge coming. But who knows, it might drop down on you. Make sure you know about your cellulose and your polythene. And let's go forward. The next thing you need to know is the hazards. Talk about the hazards. Which part is the sweet part in this pen, boy? Hazards. Hazards of electrostatics. Can somebody tell me the hazards? Some people quarreling in the chat. So that forehead is a hazard. King Jamal T. I see you, bro. I see you. Right. So we have lightning. Maybe I could put this in another color. What else people seeing? Death, lightning. I need you to be specific, not just death. Be specific with it. Explosions in flammable environments. So, flammable environments. For example, a lot of my jeans pants build up static electricity real fast. So like if I sit down on a chair and it has cloth, somehow the friction of that cloth, when I get up and I touch the door handle, it's like zzz, there's immediate thing. So every time I come out of the car now, I make sure and touch the car before I fill in gas, right? Because then really what has to happen when I fill in gas? Damage to chips, microchips, sorry. Tallest subject on you. So lightning is the biggest one. I'll leave out EG. Electrocution. We're not talking about problems with electricity. We're talking about problems with static electricity. So you can't really talk about explosions in gas stations. Yeah, you can talk about explosions in gas stations. But you can't really talk about electrocuting yourself and them kind of thing. Alright, so, and then you need to talk about the applications. So what are the applications? Applications. Now remember, the lightning strikes the tallest object. Just to talk about lightning strikes the tallest object. It happens when clouds accumulate a large amount of negative charge and they have to discharge it. They discharge it in the form of lightning. So a lot of people are mentioning the applications there. You all could have a read at them. We could also talk about static buildup here, which would lead to these same things. Static buildup. You want to use that term. when you're explaining this in your exam, the static buildup of electrons, maybe in a vehicle as it's driving along the highway, or on your clothes, cause a spark in a flammable situation. So applications, people say photocopying, yes. Photocopying. What else I seeing? Lightning rod. Well, you use the lightning rod to avoid thing. There's something I wanted to say. Where's the spray painting? Dust precipitator, right? Dust precipitator. Dust precipitator. Crop sparing. Anything else? Yeah, this live gonna be available after lint removers. Lint removers. I know I'm blocking some of the text there. Trying to get my pen to work. Lint removers. Okay, I'm taking that. Begging. Painting. Right, we're taking that. So you all know your applications. Know how to describe them too. Don't just know them. To see them. Know how to describe them. Y'all, please, no fighting in the chat. And I realize I'm not watching the chat and people correlating to each other and all kind of thing. I will do atomic physics sooner or later. So that's the end of electrostatics. Let's move on into current electricity. But before that happens, maybe we can take some questions. I'm looking to see what kind of questions. Is anyone start drawing questions? Could you predict what would happen if we have a plate that is positively charged and you have a point negative charge here? Can you predict what will happen? Write it in the chat. Must be able to explain how like lightning works and what are the steps you'll take to remove, reduce the lightning hazard. Can you explain lightning? Yes, I will explain lightning. No, they would not track. We join the field, we join the field. So remember, we can expect something like this taking place. Which direction will the arrow go? So the next thing is to explain lightning. I'll explain lightning and how we'll get right. So that's just a question. That's just a kind of weird question. Now, what would happen if we have lightning striking a building? We can have fire, right? So to avoid that, they include a lightning rod. And how does the lightning rod work? The lightning rod works by the principle of induction, like this. Imagine this is your lightning rod. Let me draw it in orange. This is your lightning rod. As the high negative charge from the lightning comes down, right? What's going to happen is going to induce a positive charge here. Now, how is that going to happen? Because this rod was minding his own business and had a nice neutral setup. Electrons all over the place. Normal. Net density is even with electrons. But as soon as this high presence of negativity come around here in the air, all them electrons going and dust it. And because this runs down to the earth, these electrons will end up hitting here. Why will they end up hitting here? Because only positive charges will be here now. Well, not only positive charge, but a high net positive charge. So it's going to actually attract the electrons. So it's like this. induction and explaining all these things work just like this. Listen to this example. It's like a girl really loves a boy, really loves him, but he doesn't love her. He doesn't love her. So he kind of, okay. Now, let me not explain it from the girl perspective. Let us make the girl not liking the boy. This is the girl here. She doesn't like the boy. She's going along his way, her way. But because she is not paying the boy any attention, he actually opens up to her. And now that he opens up to her, they get accepted, right? They get accepted. So there's a principle. There's a principle that's going on here because the negative charges actually cause their own attraction. These negative charges are responsible for everything. They chase the electrons away in the lightning rod, and all of a sudden there's only positive electrons there. Bam! So they're attracted to them. You have a girlfriend. Best girl come out. She chase away your girlfriend, and now you're attracted to she. Something so going on in this induction process. So that's it for explaining lightning and lightning rods. Also know how lightning forms. You can just do a little research on that. You have something similar to that in class here. So a lot of teachers may explain using that technique. So let's go on into current electricity. So current is actual flow in the wire. All the time you're talking about static electricity, meaning static means not moving, right? But as soon as you start to talk about flow in a conductor, the net movement of electrons in a conductor, some people put up some very ridiculous comments. As soon as we started to talk about the flow of electrons, we started to talk about current. What unit do we measure current in? What unit do we measure current in? Yes, so we measure current in amperes. Amps, amperes. Amp for short, right? Alright. So, a definition for current, a definition for electric current, you must have that in your back pocket. Can we get the definition for current, please? Definition for current in the chat. Next up, we need to talk about the test for a conductor or insulator. To test to see something as a conductor or insulator, a simple circuit we could set up. The flow of electrons, yeah, that's the movement of electrons in a conductive material. That's good. Right? So, if you want to be a little better about it, you wouldn't use the flow of electrons, you say electric charge, because sometimes current could happen without the flow of electrons. Right? You could still get a current passing through and electrons not really moving, like maybe ions moving, or maybe you have a diode or something going on there. Right? So electric current, the net flow, that net flow would sound good. Net Q equal IT, Q equal IT. Now, I made a mistake there. Since electric current, Q, remember the equation we know from before, Q equal IT, and I remember this. I remember this equation by the word quit or something like that. I don't know. It's just sticking in my mind like that. Quit. So I don't know if that'll help anybody. So, and Q equal IT. So if I make I the subject of the formula, it's going to be I is equal to Q over T. So current is charge over time, right? So when I use over time, that's rate. So that's this word, the rate of flow is what I should say. The rate of flow of electric charge. So the rate of flow of electric charge. Charge flow per second, yeah. So you want to use this word, rate, when you're defining current. Rate of flow, and then you put this equation, I equal Q over T, right? So current is V over R. Yeah, but we reach V over Rx. So you finally find out what was going on with Shansi. Yeah, you can rest. Yeah, finally find out. Right, so let's keep going. We have a lot to cover. The test for a conductor or insulator, I want to set up this simple circuit here. You want to set up this circuit, bam, 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 boop, boop, bam, bam, bam. I'm putting this in a different color. Right? Which side of the battery is the positive side? Which side of the battery here represents the positive side? Which side of the battery represents the positive side? The long side, right? So the long side is the positive side. So I'll put positive here, negative here. So you see that green arrow, already green arrow pointing, you're inserting your object here. When you insert that object there, if it's a conductor, what you expect to see happening? If it's a conductor, what do you expect to see happening? And if it's an insulator, what would you see happening? So this is how you'll test for a conductor or insulator. You set up the circuit, your apparatus. What is this, by the way? This is a bulb, right? Should I say bulb there? You have your battery and you have your connecting wires. So the bulb will light if it's a conductor and the bulb will not light if it's a non-conductor. And you need to be able to test. You could sometimes test it with a coin, metal paper clip, a piece of paper, aluminum foil, and see which metal conducts, which metal does not conduct. Which object conducts. Some objects may be metallic and not conduct, or may appear metallic and not conduct. Current in metals, ding ding ding. Why are metals such good conductors? Why are metals great conductors? Answers in the chat. Presence of free electrons. Somebody, I think we have some Joules. Because they have free electrons, right? Presence of free electrons. So you understand that. Should I move on to talk about that now, boy? Should I move on to talk about that now, boys? Boys. What's the topic? Current, electricity. So we're still talking about current here. Alright, so I'm going to make the big explanation of how current really works. Not yet. So current can flow in a conductor. What else? What are some other ways current can flow? Water, inductor, solenoid, air. Electrolyte is what I'm looking for. Or, so ionic solution, so electrolyte. Or, so when you say air or water, yeah, water is good, but water is a conductor. Yeah, that's already covered here, right? So specifically water will be like a conductor. Not convection. Why you talk? People only mentioning things for heat. That's heat. We're not dealing with heat. Where's the next? Where's the last one? Semiconductor. So we have it there. Semiconductor. Now, I don't think you need to, as watching the entire syllabus before I come on the live, I don't think you need to, well, the entire electromagnetism syllabus. I don't think you need to know about in-depth workings of a semiconductor. All you need to know about it is that you have holes, positive holes and electrons. I see you all, I see you all. Oh my gosh. Positive holes and negative electrons. And some examples of the semiconducting material. Give me the examples of the semiconducting material. Chat. And electrolytes is ionic solution, and conductors will be like metals and graphite and stuff like that, right? Silicon and germanium. One of them will have like an extra positive spot. One of them will have an extra, you dope it to have an extra negative, and it will kind of hop. The positive spots kind of hop. All right. So I wouldn't go into the explanation of that. I didn't feel that. I didn't see that in your syllabus, so I'm going into that. Right? If you wasn't keep reading, I'll probably go into that. Currently in electrolytes, but you could just take a little watch, maybe on YouTube, or just watch a video of the semiconductor, a 2-minute video, and just watch it, see how it works. And that is it. So you have it in your mind. You never did doping. Doping is in the syllabus. Y'all, let me give me a little second, right? This person talking about doping. Alright, so what I'm doing here is I'm looking for electromagnetism. Then I would look to see current. I look to see if you need to know about doping. Doping. Anybody was taught doping in school? Right. It is as I saw here. You just need to know about it. You don't need to talk about doping. You don't need to know, right? In the syllabus, I'm not seeing anything with doping. The word isn't mentioned. Here's what they mentioned. State that an electric current in a metal consists of the flow of electrons, and they need to talk about other conducting media, such as electrolytes and such as semiconductors. And you need to know silicon and germanium are semiconductors, right? And that's about it. You don't need to know the inner workings of that. Not yet. Not yet. But if you do physics in Cape, we can talk about that. I'm going to meet you on the next side. So same thing in electrolytes. We know about electrolytes already. Now, I just explained to you that current is the flow of electrons, right? So if the electrons are going this way, the current is flowing that way. But this is the flow of the negative charge. Back in the days, they didn't really think that the current was arose out of negative charge. Thought it was arose out of positive charge, and there was really no way for them to get that yet. So they actually thought the current was flowing this way, and that it was positive charges flowing this way. And it now makes sense. If there's a net negative movement this way, then it means there's a net positive movement this way. So they would be in the galvanometers and everything would be indicating that. So this here is called electron current. And what's the other type of current called? The old-fashioned current. What is it called? The one that they use. Conventional current is the opposite of electrical. So this is conventional current. So if they ask you to draw a circuit, bam. Let's just say we have a little bulb there, that's all. And let's say they put in a double battery here. Bam, 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 bam. Well, you know that's the positive side, that's the negative side. And they draw two arrows. They draw one arrow, well, they won't put colors, but they draw an arrow in black, and they draw one arrow. So, and they ask you, which one represents the flow of positive charge, electron current, and which one represents conventional current? Conventional. Which one is conventional current? Which one is electron current? I can put them in numbers if you want. 1, 2. Right, so, whoa, we're getting different. I'll come to agreement there. Which one is conventional? Is purple and black. Right. So 1 is conventional and 2 is electron. So the conventional current runs from the positive side, because remember it's the flow of positive charges. So it ain't going to be there. You can run away from the positive, this positive, and run into the negative. That is the conventional current. The electron current, or the real way how current flows, it will run out the negative and run towards the positive. Good. So we understand that, right? Don't make no mistakes with that. Now there are different styles of current. Let's just do a little quick current question. But there's different types of current. There's AC and DC. So explain AC and DC whilst I write up this question. Explain AC and DC in the chat whilst I write up this question. Don't forget to press like on the live. Now we don't have we have a kind of panic vibes tonight because exams is 9 in the morning, right? So it's a kind of cool chill back live, but a lot of people will be watching this on the exam because I'm sure a lot of people probably turn on this live and say, nah, I had time, and start to procrastinate. Anyhow, so we're going with the question. The current. So we're explaining alternating and direct current there. Moving. To a wire if 20 coulombs of charge, that's a lot of coulombs, man, passes through pass. Then sometimes they say passes a point or passes through the cross section of the wire every 5 seconds. Find the answer to that. Answer for that in the chat. And yes, direct current, one direction. Alternate current, different. Right? So the answer is very easy. Now in physics, you always want to start off with your little equation. Now I would start off with this because I only learn one equation. And then rearrange it into this. Use common T for time, capital T, more for period, right? I like how they use in capital T there. So we will use common T. And for what? 4 amps, right? Okay. So AC and DC. One stands for alternating, and one stands for direct. Back in the days, the Snanny boys wanted to do direct right through, and Tesla and the guys wanted to do alternating, and there's a big quarrel there, and the Edison tried to discredit the man and thing. Alternating current is the flow of electrons that changes direction randomly, not randomly really. And direct current is the consistent flow that moves in one direction by Joule. Not really randomly. So let's see if I can pull out that neat definition for you all. AC is the flow of current that flows in both positive and negative, with direct is in one direction. Yeah, that was okay. I wouldn't use the word. I wouldn't put the word randomly. I wouldn't use the word randomly, right? So people basically have the definition there. RMS. What they're talking about, but don't go into them thing, don't go into them. AC current is cheaper to generate. Yes. And I don't think you need to know why. Really don't. Think you need to know why. Once again, let me just peep the syllabus and see if you need to know why. For CXC. Right. So you don't need to know why. Alternating current doesn't lose as much heat in the wires, right? Because you're going backward and forward. It's easier to send an electron backward and forward like this. Send the current backward and forward like this instead of sending it continuously in one direction. So we already, some people jump in late and miss some of the definitions. Electric current is the rate of flow of electric charge. Yes, so instead of using the word randomly, use the word periodically. So that's the word you want to crack, to chop down when you're using alternating current. Alright, so let's move forward. Test for alternating. You should just know what happens. Oh yes, Lord. So you want to see alternating, you want to see this. In direct, you want to see this. Right? So we're gonna reach up all them things. We're gonna reach up all them things in justice. Don't worry yourself. You see waveforms, thing. I just want to make sure I cover all the points listed here. I want to make sure I cover all the points as I'm going up. So once let me see some Y's in the chat if you was watching right through. Y's in the chat if anybody else here right through. I've seen 300 people on the live, which is great. Right. Let's describe this. From here to here is what? What is that term? What is this term here? What is that term? Well, this here is normally V. This here is normally T. Seconds, V in volts. So that's one full wavelength. But the better word for this is period. And this guy over here, it's not amps, but amplitude. Right? So can we get a definition for the amplitude and can we get a definition for the period? Can we create one? Can you make up one? So even like if you don't find one in your textbook, can you make up one? Definition for amplitude, definition for period. Now remember, period is in capital T. Amplitude, well, you don't worry about that. Yeah, injustice, come on, like use that form 6 student, we're not going to show that. Amplitude, maximum displacement of the wave from equilibrium. State that, right? Maximum displacement of the wave from equilibrium position. So this here is the equilibrium position. The symmetrical position there, if the wave is symmetrical. And the period, the time taken for one complete oscillation. Right? So if you didn't know that, take a look at the chat. We have that down there. Cork. And there's one more equation. So far the only equation we learned was Q equal IT. We're going to bring in our next equation in the dance. This equation here, F is equal to 1 over T, 1 over T. So this is equation 2. So new things. So welcome this equation there, fellas. By the time we're done electricity and magnetism, we'll have a good few in the dance. So F is equal to 1 over T. Where F is, what is F? What is T? Well, we know F is frequency. And T is period. So let's do a question. Let's do a question. If we have AC generated at 50 hertz, what is the period for a complete wavelength? So waveform more talks about the form. So you could just plug in your formula here, but woo, that writing sucks, man. So I'll read it. AC is generated at 50 hertz. What is the period for a complete? What is the period for a complete wavelength? Don't worry, we're gonna do some more complicated question just now. So the period, you can use it interchangeably. You could swap these two, right? The F could go there, the T could go there, wherever. So this is 1 over 50 hertz. Make sure this in hertz so that your answer could be in seconds. And everybody gets 0.02, right? Seconds. Let's pull up a little harder question. Can I get a harder question now, man? Let's create a question with a diagram then. So I have V here. I have T here. I'm drawing my wave here. Let's draw a little more. Let's make it unconventional. What this book has here. If I can get this drawn properly. Let's see, this is 0. And this is 0.04. This is 0.08. It's time in seconds. As these individual spots. So, what is the period and what is the frequency? What is the period and what is the frequency? It blurry. It blurry night. It blurry. Turn up the quality. Are you seeing it blurry? Let me check my internet here and see if it's blurry. It's fine. So, period and frequency. Now, I remember doing I do about 3 past papers on YouTube already. So you can search Cohen Springer Physics and you'll see past papers. Everything looking nice. Oh, it's looking real clean, boy. It's like one of the cleanest I see it looking. I must use more colors in the life, man. Nice and clean, fresh and clean, crisp. So, the T, you'll have to use your eyes and pull out the T here, right? The T actually is you're looking for one complete waveform. So sometimes they might be a little sneaky with that, however they do that. Bam. Now a complete wavelength is from, okay, a complete wavelength could either be from, if they ask for the definition of that, and they might ask for that in waves, from trough to trough or from crest to crest. That's the best way to define it. Right? That's the length of a complete wave, from trough to trough or from crest to crest. So we see that the T here is 0.08, which means frequency will be 1 over that, which turns out to be 12.5 hertz. Right? According to the chat there. Now, before I do this, alright, F is equal to 1 over T, just to make sure you get your formula marks there, and you'll be good to go. You'll be good to go. Alright, any problems with this? Why is in the chat? I don't think this will come any more complicated than this. Just remember this equation in case, right? F is equal to NE. Yeah, I didn't put in that one in the equation thing. We also had F is equal to N, not F, Q is equal to NE. Now F is equal to NE. When I say F, what way? The N is the number of electrons, right? How I get 0.8? 0.08? Well, is the distance for a complete wave to take place. Some people still don't think it's right, so you get 0.08. All you understand it now? All you understand it now? The next live I'm going to do would be on waves. So you'll get through the optics, say light and waves and things. Yeah, so it's just a complete wave from 0. Sometimes they might start it on not 0. So look out for that. You just take away if they don't start it from 0. You just want how much pass here, and I think 0.08 seconds pass there. That enough. We can't take too long on this. We have a long night ahead of us. Let's look at electrical quantities now. I think we have next. Well done. Electrical quantities. So what are the equations we covered so far? Can you tell me the equations we covered so far? Q is equal to IT. Common T, I keep putting capital T because this book has capital T, by a custom with common T for time. We also had a next thing for Q, in case they give us this weird one, NE, where E here is the charge on one electron and N is the number of electrons, sometimes written as common Q. Sometimes they'll write this as common Q, right? And we just introduced this new guy. Yeah, we just introduced this new guy for frequency. It's actually 1 over the whole time period. The whole period for the thing. So time to take in some new ones. So this is what we have so far. Time to take in bringing a new one into the dance. V is equal to E over Q. Now I never learned this equation like this. As a matter of fact, I never really learned this equation. I learned this equation like this because I like to start all equations with E. EVQ. That's how I learned the equation. And to hell with them with the other thing, right? But we just teach it from V is equal to E over Q. Can you tell me what the E and the Q stands for? E and Q in the chat. E is equal to E over Q. E stands for what? Q stands for what? Well, we already know Q stands for charge, so I don't need to say that. What does the E and the V stand for? Right, so the E is energy and the V is voltage. And the V is voltage. Yes, no. Did I miss out anything? Right, we're good to go. So this is the new guy we're introducing, and we'll introduce one more new guy. This is all she should mention. Yes, well done, Injustice. But I find out who you is, and you come and you do a live with me, boy, because like you really know your thing. E is equal to I squared RT. Now I didn't learn this like this. I learned it like with H. Because most of the times you're using this equation, you're finding energy lost in as heat or something like that. So H here represents the energy for me. And I just learned heat. I'm just telling you what I learned to remember this equation. Heat. And I just remember to square the I. Right? So that's the next equation you want to take in. But learning this equation, not very, very necessary. I might as well tell you the very necessary equations. P is equal to IV, Q is equal to IT, V is equal to IR, and E is equal to VQ. Those are the big boys. Learn those. Right? Learn those. So everybody had those equations down safe and they know what each symbol they mean. Let me see some Y's in the chat. So Y. P as in power, yes. P is equal to I squared R. Yeah, but you don't need to learn anything else really. Once you have these equations, all them I squared equations and thing, it's just a combination of these two equations. If I want to get rid of the V, let me just show you what I mean. For example, if I want P in terms of I and R, if I don't want no V line in there, well, all I'll say is P is equal to I, and instead of V, I will write what V is. IR. So P is equal to I squared R. So all of those kind of derived, or some of these derived too, but I'm telling you, these is the equations you just want to learn. Just these guys. You have a few more equations to learn, like the equations for resistance in parallel, resistance in series, and maybe something else slipping me or something. But these is the key here. The key to set the people free. Right? So just take a good look at that and you're good to go. And actually in a question, and a concept you must be sure about, a concept you must be really sure about is that power is energy over time. Yeah. So this comes from straight from the first part in physics, right? The first part, power is the rate of change of doing work, right? Work done over time taken. So with this concept, you can mash up with, once you have this and the big boys, you're mashing up any equation. Because sometimes they might ask you, you might find out the electricity, the energy, sorry, and they will ask you the power. So now you know to use time, right? We'll see as we get into some questions. And some people are putting the ones so parallel and in the chat. Very good. Very good. Very good. Very good. So somebody say next, meaning so we understand. They beat it out enough. Let me move forward. All right, let's move forward. Ding 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 ding. Let's go. You know, you need to know energy conversions of different appliances like electrical stove, electrical heater, the light bulb, and the motor. In the motor, electricity is converted to kinetic energy. In motors, like a fan, electric energy converted to kinetic energy. Obviously, in your light bulb, electric energy converted to light energy. In your heater, electric energy converted to heat. In your stove, electric energy converted to heat. So you know a little basic conversions. That is easy thing. That is an X. I'm not talking about no engine here. Fire about that. Dim 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 dim. Right, so you're ready for the big boy. Ready to explain how potential, the best way I see to explain potential difference is this. So excuse me, okay, let me look to see if I can pull the diagram from the internet. Potential difference, waterfall, water analogy, images, map, right. Now, okay, we can look at this one. Save. So, as I said, the technique for learning chemistry, when we chemistry exam pass, was what we did in that live, and I really condensed everything into a nutshell and just kind of cram it in your mind. Learn off your exceptions, the rules, you did see that equation, boom, boom, bam, 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 you have it. The technique for learning physics is to try and understand each topic to the best of your ability. The more you understand the topic, the easier physics become. So physics is not really something you want to approach from a cram-off perspective. Same thing with maths. You had to do real plenty questions with maths. Physics and maths kind of like each other like that. You don't want to approach it too much from a Kramov perspective and approach it from a try and understand everything perspective and then learn some questions perspective. All right. So let's try and understand what is happening here with potential difference, because some people see potential difference and current and they struggle to understand the difference. Let me just see if you all see in this diagram properly. Yeah, man, see that properly. Now this is an analogy. This is an analogy here of what is happening in an electrical circuit. It's an analogy of what is happening in an electrical circuit. Now let's look at the circuit first. We have the battery. They went and draw the whole battery. Long side, short side, right? Because this is the positive side, this is the negative side. It's like the battery is giving the electrons a push. It's actually pushing the electrons out. Run so. It's going to come here and use up in something, some device. Now the electrons are going to use up and burn away and disappear. The electron just going to lose. It's just going to lose some electromotive force. It's going to lose its potential difference. The energy you sent it out with is being lost and being used to spin the motor, to light the bulb, to heat up the heater, and then it's coming down here. Alright, so let's see how this analogy helps us to understand this. This pump here works like a battery. The pump, now notice the water will never run, the system would never lose water, well, evaporating, but assuming no evaporation, the system will never lose water. The water is always here. The water is the current. The water is the electrons. The water is the electrons. They don't go anywhere. But these electrons here don't have the same potential difference as these electrons over here. How do these electrons have a higher potential difference? Because they pass through the battery and they get boosted up. They get boosted up, and as they fall, they get used up in the motor, the light, the whatever, and they get a low potential energy, potential difference now. So they need to come back into the battery, beat out and weary. Alright, we reach back, fellas. But there's the same current, because it's the same amount of electricity, it's the same amount of electrons, but they have less potential difference. So I want to see the words and the diagram. So you're fighting up a little thing, do the movement, right? This works like a supercharger. No, this is important, and trust me on this one. This is important to understand this. This is important to understand this. It makes getting it real blurry. Let me check again. Why people saying it blurry, boy? I seen everything. I seen all the words, everything. So go in settings and change it from 480p to 720p. I think I'm streaming actually in 720 or 1080. It's not blurry. Alright, so that's the analogy here. We start to see this play out in different ways. This is important to understand to figure out what will happen in a circuit. Like if we have a battery, why is it that the potential difference here is low and the potential difference here is high, but the current is the same throughout? Right? That's important to understand. Or why is it in a parallel circuit? If you understand that analogy really good, you'll understand why in a parallel circuit the potential difference from here to here is the same, but the current in each branch is different. The current splits up. It's because the water is the same amount of water going through. It's almost like if instead of this we had more windmills or whatever the hell that is, with the water falling out here. You have the same amount of electricity here, the same amount of current, but when it reaches this junction, some had to go so and some had to go so. But from here to here, the same distance, is the same like height it have to fall. So it will have the same potential difference in all of the branches, but it will have different amount of current. So hopefully you kind of see a little clarity there. Let's start going to some memorization and understanding of questions, yeah, and blah blah blah. All right. Sure. Let's see if I can find a question. So I'm going to write a question here. It takes a little while to write the question. So you will just be watching me writing this question right now. A current. This is not a current. This is not a resistance question. Let me coming into the resistance question just now. Current. This is a question involving one equation of 3 amperes flows through, you're reading that, a wire with resistance, for 5 minutes. For 5 minutes. If the potential difference PD across the whatever the wire is 5 volts, how many, so I've seen people talking about things there, joules of energy was converted from one form to another. Was converted. Right, answer this question. Right, so 450 joules, Joule per sat straight out the block. Somebody get 500 joules, second person on the block. Injustice get 450 joules. Well, you know, Joule and Injustice running things in this topic right now. Let's see if anybody else can get some more answers here. 450 Shivani. Amansi, you don't even know to start with this. 450, 450. Now, a lot of physics calculation involves taking one equation, figuring out something, plugging it into the next equation. Like 100% of physics feel like that. And after a while, it starts to get boring. Well, you wait to get boring, you wait to get good. Some person say 1.5 joules, where they get that 1.5 from there. Okay, so what's the equation we had for E? First, we're trying to find what this is how I work out stuff in physics. Yeah, I could use the EVIT equation. Well, I remember this like saying EVIT, but I don't even want to use that. I want to use the equation we had. Because some people just remember the equal V over Q. So we have voltage, the wire is 5 times is 5 minutes. That minutes will have to convert to seconds. And you have the current. EVQ, sorry. Yeah. So somebody corrected me there. That's a mistake. So we have this equation. Remember I told you that them is the big equation still in. And you just pull out the one that we want. We want the energy. So you find the one that you want in your mind. This is what I would have done. So they're trying to make us find energy. So I find this equation. Now I see if, because I know I'm dealing with current and thing. So I see what missing. Do I have the voltage? Yes. Do I have Q? No. Okay, so then I need to figure out what is the equation for Q. You understand how it works? So now I'll be like Q is equal to IT. And some people know this whole equation VIT one time. They just replace this IT straight up into there. So okay, let's find Q. Q is equal to IT. Do I have I now? Yes, look, I up here. I is the current in amps. And what about T? Common T, that is. What about T? T here is time. I have that in 5 minutes, but I need to change that 5 minutes to seconds. So current 3 multiply by a block in. Well, you catch the idea now. And why is in the chat? Why is in the chat? Why is in the chat? If you understand what to do now. Next. So T here is 5 by, I'm just trying to squeeze it in, 5 by 60. So in the end, it's going to be V 5 by 5. Hey, not 3, is 0.3. 5 by 0.3 by 5 by 60. This is 0.3 from here. Yes, sorry about that, 0.3. Next, and you get whatever they get. I think it's 450 they say they get. Five by 0.3 by 5 by 60. You type down the calculator, get 450. Don't forget to write J for joules. Right, so I feel sorry for circling. You're feeling sorry. Let's go forward. So we have some good Y's in the chat there. Everybody understand that? Let's do one more similar to that. I think these are easy stuff. Do some of Fleming questions. Please come into that, but we have to go in order. What's the time? 8:37. So about 9 o'clock we might reach there, man. Nah, a little after 9. So the charge of 2 coulombs flows through a component with a potential difference of 5 volts. It passes in 200 milliseconds. So part A is what is the energy consumption? I just put consumption. Or what is the energy passing? What is the rate? Fight it now, Aaron. Stay up a little. Stay up 30 more minutes. Is the rate of energy consumption. Opal, 10 joules. Right? I seen Shah complain. What Shah say? You ain't helping anyone. I never saw you helping anyone. As me? As me talking to? Shah, you looking? If you looking, you ain't doing a good job. Have it. Shah, what going on, boy? Shah, you have something to say? Or Shah telling injustice that. Whatever, yes, I'll do all the thing, yes, whatever. So we have 10 joules, and what's the rate? What's the rate of energy consumption? Somebody say 50 watts. 50 watts is good. 50 watts is good. I seen some 0.005 where that come out from. Right? Maybe got a little unit problem there. So the 50 watts is good. I accept my handwriting is trash right now. I can accept that. I'll let go, Carolina. Let me have peace. Let me have peace. Or they multiply by 5 because, yeah, 200 milliseconds. Okay. So, anybody don't know how to do this? Let me see some. Me, sir. So, if you don't know how to do this, let me know. If you don't know how to do this, let me know. Or can I go on? Is this a next situation here? Or should I do it? I'm lost. Iran say lost. B is asking for power, yes. So anytime you see rate of energy, that is code word for power. Rate of energy in physics, in any section of physics, rate of energy is code word for power, right? And remember I told you all you just need to know the big boys, these equations here, and keep in mind that you need to understand this equation where power is energy over time taken. And normally, every time you find energy, they might just throw in that little power talk afterwards. That rate, that power consumption thing, they straight in. So just make sure you understand this equation. See how I just come and throw it in back here too? Be ready for them when they throw it in. Alright, so let's see which equation you're going to use. Very quickly here, finish off this. The charge was this. The potential difference was that. So the energy, we just use the equation straight up, right? Why am I writing on this? Use that equation straight up. Get your energy to be 10. What was 2 by 5? 2 by 5 equal 10 joules. Then we're going to use this equation, but it just had a little minor conversion to do in that you found out E to be 10, right? But the time was given as 200 milliseconds. So you want to put 200 and milli mean 1000 by 10 to the negative 3. Thanks, Shelly. Thanks, man. Thanks. And this is 50 watts. Power is measured in watts. Why is in the chat? So this little part here, this key part here, this was a conversion of milliseconds to seconds. So this 10 by 10, yeah. All right, so let's move on. Conserving energy. Conserving energy. What are some ways we can conserve energy? What are some ways we can conserve energy? Somebody say one more. So while y'all writing on ways to conserve energy and reduce energy loss, so people can just breeze through that. I'll just write out one more question. Lamp is on for 100-watt lamp is on for 4 hours. What is the cost of this given 1 kilowatt hour is equal to $0.2? What is the cost of this? Now, the key to this kind of question, good thing I say one more question because I forget to talk about kilowatt hours. The key to understanding this kilowatt hour question is understanding that this is a unit of energy. So I hope you all read all of the steal energy from your neighbors. Beg your neighbor for a drive, carpooling, right? Do lock the fridge and stop looking for food if you know it's not there. All that we take in that solar water heater, bap, 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 right? Cool, cool. Turn off the lights thing, right? Good. So somebody get 80. Well, I'll get this question from me. Thief crying from the lines, 80 cents. 0.8 cents. 0.8 cents. No. No, no, no. Oh, you're not getting no correct answer. See, I put the wrong question. 100 watts for 4 hours. What is the cost? If you're getting 0.2 cents, $0.2 every kilowatt hour. Right, so Shania Shivani correct answers. Yeah, 1 kilowatt is 1,000 watts, but that not, yeah. Oh, they forget to make the conversion. Right, yeah, that's 100 watts. So probably some people forget to do the conversion. So I'll add in one more novelty question. How many joules in 1 kilowatt hour? How many joules? So people who get 0.08 and don't understand, let's start to work out this question. So a 100-watt lamp is on for 4 hours. Immediately you want to get energy, right? Energy is equal to, now we know power. We are given power. This is power. And we are given time. And I give you the equation with that. I say power is equal to energy, like that. Rate of change of doing work, energy over time. So if I want to find the energy now, and I want to find the energy in this unit, this is what I do. Get rid of that t and bring that t up here. So I have this equation now. E is equal to P by T, where the power is 100 watts. I know what watts are kilowatts. So 100 watts is actually 0.1 kilowatt multiply by the time, which is 4 hours. And I'll get something here. Did I make a mistake? 0.1 watts. Prime chemistry. Performance. No, this is correct. This is correct. Yeah. I'm correct. I just write down the wrong thing for the question. So them have a different weekend. If you're following in the book, they have a different weekend, but we'll get our own answer. So what's the answer here? So 0.8. 0.08. Yeah, okay, my bad. So I was judging all the answer ahead of time. So this is 0.4. This is 0.4 kilowatt hour. And the cost, well, the cost will be like, alright, so at least we get a little experience with this question. And what the cost will be on this side when I finish, right? So I'll start off with 1 kilowatt hour is equal to 0.2. Therefore, 0.4 kilowatt hours, because I take this answer from here and pay there. So I'll have to multiply 0.2 times 0.4. So everybody who gets 0.08 was correct. 0.08. So I'll send so $3 here. Yeah, so we correct. Now in the question, they had three light bulbs. That's why some people get a different answer if you was watching the question. So we got to go. What book is being used? This is a kind of new book. A book, Physics for CSEC by Sam Lalmani. Next book is being used is this book. I want a GCE book. And the next book that's being used, a lot of books are being used here. Is this book. But I'm not taking questions from this book. Most of the questions are not taken from this book. Right? And apparently I'm changing up some questions. So we good there? Why is in the chat? Now, I won't say I don't like this book, it's alright. But this is the best book for learning concepts in physics. But most people wouldn't have this book because it's not, this is not CXC syllabus, this is GCE syllabus. We good to go there? Let's try this last one here. How many joules in 1 kilowatt hour? How many joules are there in 1 kilowatt hour? How many joules are there in 1 kilowatt hour? Somebody say they have none of those books. Why y'all saying why? Because I asked for why isn't it? He knew I wrong here. Why is this when we're ready to go on or you get through or something? 3.6 megajoules. Well done. Well done, Injustice. Injustice, you doing CXC physics? Because I find you speeding, brother. Oh, you had that question down look. Somebody say 3.6 Jave. Yeah, I know you. That's good. 3.6. Somebody say 1,000. So how are we going to work this out? Remember, kilowatt hour is a unit of energy. Kilowatt hour. So this is how I would work this out. This stands for 1,000 watts in 1 hour. And we know that energy is I always base this equation from this, so I'll base it from this. Power is energy over time, right? Rate of change of energy. Right. So real plenty people getting good answers there. Pretty deep. What's up with that answer, my friend? You didn't see Exodus here? It is the power of anime that have me on point. So recommend your students to watch anime. It's true because I've watched a lot of anime and look where I am teaching multiple subjects on YouTube. The key is anime, my fellas. Alright, so let's just ignore some of those conversations there. I'm just here for nostalgia. Alright, the brother Gavin, hold it down. Let the nostalgia kick in. Alright, so we have so let's just substitute in here now. I'll put the E here and put the power by time like this. Power, so you'll see what happening here already. 1000 by 1 hour. We write in seconds. So 60 by 60. This represents 1 by 60 to get to minutes, and then another 60 to get to seconds. And that's how everybody getting 3.6 megajoules. So that's 3.6 by 10 to the power of 1, 2, 3, 4, 5, and 6 by 6 will give me an answer in the 36. So it's 6, right? 3.6 by 10 to the power of 6. So 36 by 10 to the power of 5, which will turn out to be 3.6 by 10 to the power of 6. We good? Alright, Y is in the chat, and let's move on. Everybody good there? We talked about conserving energy. We talk about the use of fluorescent lamps instead of incandescent. We talk about using solar water heaters. We talk about turning off lights. We talk about using, instead of using split units, use large air conditioning systems. Right? Alright. Alright. Some earlier, I see earlier all the time here, and then always message me on Instagram, and it's get problem to connect your Instagram profile to who you is on YouTube, right? Who you are on YouTube. Let's move on to circuits and circuit components. I think that is it for reading. Let's move on to circuit and circuit components. I will draw something and you'll tell me what it is. What's this? What's that? What does this represent? A man balling real plenty day boy, and I'm a son. So this is 1, 2, 3. So it's a cell. What about this one? 4. 2 is not a switch. 2 represents AC supply, AC power supply. Well done, Pickle. Okay, so let me train this then. What about this? What about that? What is this? So just keep listing out Alt as 1, and you could copy and paste a comment. You could copy and paste a comment, and just add on a new one when you're done. When you get reach 4. Where are we on? We're on 5. What is this? Or sometimes even drawn as this. What is this? What's the difference there? 7. 7 fit. What is this? What's that? Somebody say 5. What? Right. Some people confused. Some people are confused. What's the difference between 7 and 8? Alright, so let's name them off. This is a cell, right? Battery cell. This one is AC power supply. Okay? AC power supply. This one is the cell. Cell. AC power supply. Switch. DC power supply. Number 4. Wires crossing over each other in number 5, but they're not touching. They're just crossing over each other, but they're not touching. Number 6, these wires cross each other, but they are touched. And the difference between 7 and 8, this one is a fuse. because you can clearly see the wire going through here, right? So we call that one a fuse, but this one is a, what's this one? That one is a resistor, but it's a fixed resistor. A fixed resistor. And another way we can draw that is with the squiggles like this. Yeah. So that's the next way you could draw that. All right, let's do a next set. 1, 2, 3, 4, 5, 6, 7. Let's do a next set of them. I'll join it with red. What about if I did this? What is this called? What's that? Or I could draw them. I could draw it like this with the box again, and put the arrow across the box instead. Then everybody knows what this is. If you don't know what this is, you need to just go and find a belt and beat yourself. You should know these. What's that? Right. Right. So we get 3D. We get 3D. I'll do too much numbers. So variable resistor, light, filament light actually, filament lamp. It's actually a filament lamp, voltmeter, ammeter, and a diode, and it's pointing in the direction to allow that the current is allowed to pass. Okay, all right. It's important to know that one of these is connected in series, and one of these connected parallel. So which way does it go? Which one? Is it so? Which one is connected in series and which one is connected in parallel? So the ammeter is in series and the voltmeter is connected in parallel. Because the voltmeter have a high resistance in it. Right? The voltmeter has a very high resistance in it. If you connect it in series, you'll cut your whole circuit. Your circuit will be dead. Right? And you want to connect the ammeter in series so that it can measure the entire current, so that it doesn't split the current. If you put the ammeter in parallel, part of the current will go through the ammeter and part will escape somewhere, so the ammeter won't give you the real reading for the current for the whole circuit. So wherever you want to get the whole current, you need to put the ammeter on that whole part of the excuse me, circuit. Let's draw a cell, and well, I'm not going to draw a cell. Drawing a cell is kind of hard to do. Well, you see how hard it is to draw on these things. So I'm going to pull out a cell. I'm going to talk about it. A battery cell. Why this man is... Why? Spare me now, brother. Spare me. What? It's the same thing. So this went into great detail that we don't really need to go into, but I like the diagram. The diagram is very nice. So I'm going to shade some parts. I'm going to shade some parts that I need to be able to label. This is a zinc carbon cell. Which side is the negative? Which side is the positive? Top or bottom? Which side is the negative? Which side is the positive? We come into all them things like transformer and all kind of thing. Don't worry on yourself. This song is like all you're worried. But already reach a good way. And we already have a good way to go. I would say we reach about halfway. So the top is positive, bottom is negative. Where is the electrolyte located? Where is the electrolyte located? If I was you, like before the exam, I'd draw one of this. So maybe tomorrow in the day, you'll take your time and just draw this battery cell from a textbook, the one that I need to draw from a textbook, so you can label everything. Take your time and draw it. It will only take about 15 minutes to make sure you have this just in case. It's better to over prepare than to under prepare, right? So the electrolyte is the brown, very good. What do we call this? What do we call this? This part here is the carbon, right? The carbon electrode. And where's the zinc? Where is the zinc though? The zinc is on the can itself. Not on the protection, eh? Not on this not on the thing that's separated here. The zinc is on the can itself. It's on the can itself. So let's talk about it. Talk about the zinc, talk about the carbon rod, talk about the electrolyte. All these things you need to be able to talk about. The separator. None of this coming, just for kicks. Yeah, is that just for kicks here? The seal. The jacket. And the conductor. I'm doing the multiple choice for everything, but it's not multiple choice time yet. No, the contacts. So is the zinc the positive or the negative electrode? Which one is the negative electrode? Which one is the positive electrode? So you could do SHC. What is SHC? So you're doing any multiple choice? Yes. Some numbers printing. You have to be a good idea to cheat and see like C maths. Sure, don't blame the whole school. Don't blame the whole school. There's one man we call tag boss. There's a lot of students actually, but not like the whole school. There's some dumb students, not the whole school. Don't kill off the whole school. I'm sure the school had good students just like you as well. The zinc is the negative, so the zinc is the anode. And you already should remember from chem, the anode is the negative electrode. And the carbon would be the cathode, right? So you know the carbon is the electrode in the center that going straight up. So that's the cathode, that's the positive side. That's why it goes straight up here, right? What about the electrolyte? Where's the electrolyte? Just remember this ammonium chloride. And you don't need to remember the chemistry of it. Just remember that it causes the ions to move. It promotes a reaction that causes the ion to move. Somebody said, no, cathode is negative and anode is positive. No, that is not correct. What? Anyhow, take a belt and spank myself. Cations go to the cathode. Yes, cations go to the cathode. The Jackson has to be positive. Right, yes. The whole chat jumped down on me there. I just watching my chat explode on top of me here. What did I say? Let me get this diagram of the thing in the textbook. What did I say? Battery diagram. Yeah, hang on a second there. I'm gonna find this battery diagram before they half kill me here. Um, what did I see? Negative, zinc can negative, carbon negative, attract the positive. Right, yeah, okay. Cations go to the cathode has to be negative. Anions go to the anode has to be positive. You feel I know people, you said the anode is negative. I said the anode is negative. Cathode is negatively charged and attracts cation, right? But the anode here, right, even though the anode here is negative, even though here the anode is positive, sorry, it leads to the negative pole on the battery, the negative spot on the battery. Right. So we know the thing that ground us in this in chemistry and physics is that the cations go to the cathode, the anions go to the anode, and that will let you know what happened, right? For cations to go to the cathode has to be negatively charged. Right, that's great. But in this here in the battery, the cathode the what I want to see, I lost my train of thought. This here is the positive pole, although this carbon here represents the cathode, although the carbon represents the cathode and is negative, this here leads to the positive pole. You understand what I'm trying to say? Oppositely charged, yeah. So that is that. Yeah. So on this, go to transformers. Alright. Let me don't waste no more time on this. I'm not too sure this on the syllabus. Let me just take a little look. To see if I explain everything on the syllabus where this is concerned. Just checking, guys. Okay, look like I X out the syllabus. Right. So I'm scrolling through here, looking for this. There's batteries on the syllabus. Map magnetic field, data, magnetism, logic gates, electricity in the home. Not really seeing that. Man, just want me to reach transformers. We come into transformers, we go into IV relationship now. Just the parts of the cell and mention y'all, it's on your syllabus. It's on the syllabus. But I think we mentioned everything we need to do. The functions of each of the thing. No, we didn't mention the function of the separator, the seal, the jacket. So let's just quickly mention it. So the separator is a gel piece. It separates the anode from the cathode. Yeah. Right? Separates the anode from the cathode, but it allows ionic conduction for the ions, for the electrolytes, right? But it separates them. And the seal stops evaporation from occurring. A man say battery tastes nice. I've seen people falling off the life. The seal stops evaporation from occurring. The separator separates the anode and the cathode, but it allows conduction across the it allows ionic conduction to occur. The seal stops evaporation, so electrolytes don't dissipate because it kind of is a piece. And the jacket is just for strength, and the contacts, that's the terminals on the battery. Right, so the keyword here, the separator is separates, and we're done with this, separates, but it allows ionic conduction. Keyword here is prevent evaporation. prevent evaporation. With the jackets, this is for strength. And the contacts, these are just the terminals. Why is in the chat? If you're ready to move on there. What's the difference between primary and secondary cells? Well, I've seen some ends. Alright, for the people who have ends, just go and check the diagram and practice it in the textbook. So lithium batteries. No. Primary is not rechargeable, secondary can be recharged. So rechargeable. And I think that's about it you need to know. Examples. Where's an example of a rechargeable of a secondary battery? Or secondary cell, I should say. Example, lead acid, right? Car battery. Or a phone battery, lithium. Let's call it lithium ion. And examples of primary cells. Disposable batteries, which we just draw one of just now, right? Zinc carbon. Alright, so we're ready to go there? Now, is these kind of things you don't want to overlook when you're revising and you're trying to get your one and or you're trying to get your merit or your all A's. So you revise all your calculations and things and you just kind of overlook these things. You want to make sure, because it's the little 1 mark and thing that you will lose off if you just forget the definition of primary and secondary cells. So if you just forget your examples, them little things is take away your little marks and make it a shine for the people. You want to shine for the people. Alright, mercury oxide, great. Charging. You could get a question on charging a cell. You just need to know how to use the same formulas from before. Alright, let's do a question, but we're going to involve resistance in it. By the way, what is Ohm's law? Let's go on into resistance. What is Ohm's law? Ohm's law in the chat right now, please. Ohm's law. What is Ohm's law? 9:20. So we may finish all of this at around 11 o'clock or 11:30. What is Ohm's law? Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the right. So we Ohm's law. Know your Ohm's law. People saying it there. What else you need to know? What is an ohmic conductor? What's an ohmic conductor? Very straightforward to answer this question. What else, boy? What else? What else? Somebody saying 11. 11. People want to go whole night, or? That's how I sleep and download this video tomorrow. Nah, stay up and get it one time. Don't procrastinate. Stay up and get it one time. So if you just put the formula, you will get it correct. No partner. If they say to write a definition for Ohm's law, you better write a definition for Ohm's law. Sleep is for the weak, rest is for the dead. Explain commutator and logic gates. We come into that. Hold your horses, my brother. But the logic gates part, yeah, we come into that. Come into everything. We're gonna do every single thing in electricity and magnetism, right? So when I've done this video on electricity and magnetism, I've done everything. I can tell people just go and check that video and their physics on Monday. Alright, so I think I could probably hit a little question. I'll read out the question first. Nah, not too easy. Not too easy. Not too easy. But we'll do some questions when you come across the series and parallel. So you must know your little your diagram. You'll see diagrams for filament lamps, diagrams for ohmic conductors, stuff like that. Copper sulfate solution. The copper sulfate solution is do this one. Why it have the space here in the copper sulfate solution? This is your current. This is your volts. Why is there a space there? When you have your copper sulfate solution diagram. Back EMF. Alright, explain. Tomorrow is not physics. Physics is Monday. So this is like your copper sulfate. This is like a copper sulfate solution. You know your ohmic conductor is like this. This is your IV diagrams, what we call the IV diagrams. This need to pass through 0. And you know your filament lamp. I think that's all you need to know. Your filament lamp will be like this and then curl down like that. Right? Filament lamp works like that. And there's also a little back in the filament lamp to do this if you're using a reverse voltage. The reason to have this little part here is because you need to overcome an EMF first, right? But I don't think you need to explain that in CXC. So after your voltage reaches a certain level, it's only after you cross a certain threshold level in your voltage, current can start to flow. So once again, I'll just draw them very quickly here. I'll draw it in black now, all of them. And you'll tell me which one is which. There's this kind, there's this kind, there is this kind, there's this kind. Oh boy. I need to put this one. So like the red day, like the red day. What there's all of these is IV diagrams. This goes so. This one goes like that. So 1, 2, 3, 4. 1, 2, 3, 4. Chat, answers in the chat. Label each of those IV diagrams there. And by IV I mean current against voltage. IV diagrams. IV diagrams. IV. So this could go down so too. Yeah, so 4 is a diode. 1 is the ionic solution. 2 is a metal wire, a ohmic conductor. And 3 is the filament lamp. So everybody have that there down. It's in the chat. I said also. You need to know your IV diagrams, be able to label them. If it comes, it will come just like a little simple thing like that. And if you don't know it, you lost the mark. Right? And you need to study on how to do the hard stuff, the calculations. Make sure you can do the easy stuff, right? So let's prove resistance in parallel versus resistance in, look, we reach here, boys, we reach here. So we know resistance in series. Give me the formula for resistance in series. We normally use T here. And then give me the formula for resistance in parallel. Formula for resistance in series, formula for resistance in parallel. Can I have them, please? Alright, so in series you add up. Hey, somebody saying something crazy in the chat there. This one is the series. This one is the parallel. Right, so in parallel, you have this situation taking place. And then you end up with an add and a divide thing. Add and a multiply thing. Now, sometimes you can have 3 resistors. With that 3, you know what to do. So what? So with that 3, you just add on here. You kind of need to have an idea of how it came about. Who knows, you may be asked in like a question 1. That would be a real nice question 1 for them to bring, like where they show you it and you kind of break it down and figure out how it come about. So it comes about because you need to figure out what adds to what. So alright, let's start off with the series. So in a series circuit, let's draw a quick series circuit here. And I'll just do the 2 items. As I said, you can have 3 resistors or more, right? The voltage here, we'll call that V1. The voltage here, we'll call that V2. And the entire voltage, maybe I should put that in different colors. Pay attention, this is kind of important. V1. Well, I've seen lots of people going to sleep. I saw more energy than all your boy. First, well, not these who stay in here, but I saw more energy than some of the and that shouldn't be because I just hit 30. Someone really young. They're supposed to be able to grind, man. So VT is equal to V1 plus V2. Because in series, you add the voltages. Because you could think of it like the waterfall. You go down one bump, then you go down the next bump, it's losing energy. Now you just substitute with this. Remember, V is equal to IR plus IR1 plus IR2. This V here is the same as IR, the total resistance. Now if you notice, you have I here, you have I here, so you can factorize out the I. Why isn't the chat of this making sense? For the chemistry exam, I write my name in the school name section. I was so excited. Alright, now the reason why I's, you don't have like I1 or I2 here is because the current in series is the same throughout. Current is the same throughout the series. It doesn't matter if you take the current here or here, it's the same throughout. So I can just factorize out the R, cancel R from everybody, and I'll end up with the formula. RT is equal to R1 plus R2. So you old is such a harsh word, man. So let's draw the series. Let's draw the parallel, I mean now. So we have this one item there, and we have one item there. And that's going towards the battery. Obviously this will not come back and hit the battery, and I didn't draw that, right? But who cares? So now from here to here is VT. We can't use V because the voltage is the same here, so we can't use V to start off the equation. What we need to use is I. The current here is IT, and then the current in this one is I1, and the current in this one is I2. So we're using I to start off the flow. So it'd be like IT. You see how we start off with V when we are starting in series. Now we need to start off with I. So it'd be like IT is equal to I1 plus I2. So if they ask you to derive the series equation, can we use that? Obviously, this is what you have to use. This is exactly what you have to use if they ask you to derive the series equation. Get Cohen to 30,000. Yes, get Cohen to 30,000 subscribers. No stamina. I have no stamina. So you in IT? Hopefully, I have the stamina to do IT, because when I was watching IT, I was like, whoa, so much things I forgot in IT. I cannot believe I need to memorize all them acronyms and things. So hopefully I might help all in the IT and in the programming, right? So now remember we substitute V is equal to IR here. But since V is equal to IR, I is equal to V over R. So this is why it get upside down like this when we go into parallel. I is actually equal to V, and I don't need to put anything for the V because the voltage is the same. RT over V R1 plus V R2. And when I cancel all the V from everybody, I'm going to end up with 1 over RT plus equal 1 over R1 plus 1 over R2. So it's pretty easy. It's easy. Yeah, I've seen people saying it easy. And that's how we derive those two lovely equations there. You need to know which one to start with. And the key is to use this equation. V is equal to IR. In series, you start with the voltage and you add it up. And then you substitute using this equation. In parallel, you start with the equation with I and you substitute using this equation, but make I the subject of the formula. Y is in the chat. Next. So then you need to use that information to solve questions, right? Let's draw a little diagram here. That's your question. Drop a diagram. Ask the people them a question. Calling this one 1 ohm, 2 ohms, 3 ohms, where ohm being the unit to measure resistance. I1, I2, I3. Because remember the current splits, right? It splits into 3. Whoop, whoop, whoop. Current split into 3 there. So we put IT here now. Current going this way, coming back up here. Hey, this needs a battery. Let's make this the long, short, positive, negative. No, but you don't need to have that there. Alright, so let's ask some questions now. What's the total resistance? Total resistance in the circuit. So I've seen some people say 3 and 2, some people say 2 and 3. Zibidaba dibidaba. If you're following from the book, a next mistake in the book again. We're really going on here, boy. And I love this book, you know? I just buy this book not too long ago. So I get to check it through and see the mistakes. I seen 6 ohms, I seen 0.54 ohms. Where it really is, boy. What's the total resistance? Like, what's the resistance in the whole circuit then? This number here is 1. Alright, so let's just work it out. 1 over RT plus 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over RT is going to be equal to 1 over 1, so that is 1, plus 1 over 2 plus 1 over 3. What are we getting there? One and 5, 6. 1 and 5, 6. So 11 over 6. But this is 1 over RT though. So we need to do a little swappy. We get 6 over 11. 6 over 11. A lot of people stop at the 1 and 5, 6, you know, after we just talk about that though. Somebody say they lost. Maybe we need to re-explain this. I can't do this. Somebody say they can't do it. Why people saying they lost? Why do people don't say how you do this? Well, you know I have a problem with that saying you lost. Why are you saying why you lost? Why are you saying what is that? How you lost? How you lost? Where you lost? Which part? Say which part? You don't understand which number, which line. How am I going to pass? That sounds too depressing, man. What is MP0? That's easy. Some people say that's easy, but some people apparently have problems with it. The LCM, you lost the LCM. And the current getting heated. I'm not getting heated. You should see me in class. I'll be current these students. Don't tell me I lost. Show me which line. What is the line? And then when they tell me the line and I explain it to them, I'm like, you see, you see, you see. What is the I can't handle the defeatist mentality. You need to be more positive. People ask me what is impedance. Impedance is the total opposition to the current flowing in an AC circuit. Flowing triggered. And they fully done so. No, that's a comment I read there. Flowing chill. Flowing. Where did you get the 11? Where I get the 11? Right. Plug this in your calculator and you'll see 11 pop up. So, you see I can answer questions I can't answer when you see you get lost. Alright, let's pull out my calculator here. Yes, that's only the total in the parallel section. But the parallel section is all that. Add up the resistance here, here, and here. And that means that's the resistance in the whole series. That's how it works. There's no resistance. There's no resistor here. Now, if I had a resistor here, like if they draw a resistor here, that'd be some bacchanal. Hey, if I draw a resistor there, it means after I work out this and I get this number, I need to add it to whatever this is. So, maybe I'll do that question there. So, this is 1 and a half and a third, a half, 3 over 6, plus a third, 2 over 6, 5, 6. So 1 and 5, 6. 1 and 5, 6. Is this correct? 1 by 6. 6 plus 5. So this is 11 over 6. Right? Fractions. And then this is 1 over the total. 1 over, so if I inverse now, I need to, people saying inverse it. I cool it down. You can use that word. If I inverse it, in other words, if I flip the numerator and the denominator, this side must flip the numerator and the denominator. Any more questions? Any more questions? Any more questions? So I'll give you our next circuit and we'll try and work out some stuff. Take our next circuit now, fellas. Take our next circuit. Let's make it similar to the last one. But let's do what I talked about just now and put a resistor here too. Let's make this resistor 1 again. Let's make this one 2. Let's make this one 2. Let's make this one 3. What is the total resistance? Rush it. Let me see who will finish first. What's the total resistance here? So we're going to talk about fuse after, and after we talk about fuse, we are going to talk about electronics and logic gates. So after fuse, we're going to talk about logic gates. After we finish with logic gates, we're going to talk about motors and generators. And after we talk about that, we're going to be done. You understand? We're going to be done. So we're getting different answers. We got 3.5, but Joel was the first one to pull out at 3.5. Wow, Joel, you inside my mind or what, buddy? Somebody say a half ohms. We're getting different answers, but we're getting 5, we're getting 3.5, we're getting a half, 3.5 kind of reigning supreme now. Kicks pull out at 0.4 and then kicks when you pull out that way. Logic gates, finally I could relax. A man was tense all the while, just waiting. Well, how long this going on? 2 hours and a half. 2 hours and a half this man just sit down. So when the hell this man going to talk about logic gates? So what passes you got? Yes. That's the answer to the question. So what passes you got? Yes, that's the answer. 3.5, 3.5, 3.5, 3, 0.8. When people ask me, so what subjects you teach? Yes. 3.6, 3.5. Why people getting different answers? They work it out, right? So you need to see, if you got a question like this for CXC, you need to work out one part first, then add on that thing. So let's work out the parallel part first. So the parallel part here, so I'll put RP to represent the parallel part, will be 1 over 1 plus 1 over 2 plus, and I'm just using the formula, right? I'm put in the formula first, so I wouldn't be like bluffing my way through. So this is R1 plus R2 plus R3, what the hell? Plus R3, what the? 1 over R3, so this is 1 over 1 plus 1 over, is that a bug of it? Well, let me get all passes. 1 over 2 plus 1 over 2. So this is 2. Well, 1 over 2. 1 over 9. So we get 3.5. 1 plus a half plus a half. 1 plus a half plus a half. 1 plus a half plus a half. 1 plus a half plus a half is 2. So the resistance in parallel is equal to a half, because the other invert that's over. So do IT next, please. Logic gates is in IT too. So give us current in each resistor. Question, please. All right, I'll give you a question with a little harder stuff involved. Can I pull out one from here? And there are one for the people, them boy. So I've got one for the peoples, them. So I gotta make up that question. Alright. But yeah, so people pulling back now to 3.5. And therefore the total resistance now would be resistance in the parallel. All of this could represent by one resistor, which is half. And now it's interesting to note, I just want to point out something. Plus that third resistor, I put 3 here, but I will call this resistor 4 or something. Resistor 4. So this is a half plus 3, because it's 3 ohms. So 3.5, right? Everybody see how we get the 3.5? 5. Y is in the chat. So there's 3.5. Now it's important, I didn't put the battery and all kind of thing, but nobody cared about that. It's important to, it's kind of interesting to see that this is 1 ohm, this is 2 ohms, and this is 2 ohms, but yet when you add up the total resistance, it comes out to be a half, less than all of them. It's interesting. It's interesting. So when you start to put things in parallel, it's make it easier for the current to pass. Even though you increase the resistance and you put it in parallel, the resistance is dropped. But resistance in series is add up. Is add up pretty high, man. Alright, so he wanted a question involving like current, so we could get some more out of it. Now remember, I don't teach physics right through. Like I have a few private students and I just teach them the hard things, because the private students kind of, they update now, boy, they update. So I just teach them like motors and things. So I'm really making up these questions every day, like in maths. Let's not do the same circuit again. I fed up to see that circuit. So let's create this circuit. Let's make you red too, my friend. Let's draw the circuit to look like this. Let's just put 2. Let's erase this. I'm creating the question here, guys. That's not a fuse, that's a resistor. Another resistor there. Let's put Let's put a resistor here too. Now, let's not color the resistor like that. So let's waste some more time and erase it back off and draw a box. Wow, Cohen, really performing here, man. Bap, bap, bap. Let's see this resistor. It's 2 ohms. 2 ohms. And let's say this one is 3 ohms. Let's say the current is the current in the circuit here. Total current is 5 amps. Let's make this. Oh gosh, it's taken so long to make this question. Let's make this. Let's make you 1 ohm now. I will change up the question to suit just now. So the current in the circuit is actually 5 amps. And they want to know what is the reading on the voltmeter there. What is the reading? So what is V, or what is the total voltage in that circuit? Proceed with caution. So if you see a question like that on Monday, how would you do it? So people are pulling out how much ohms and thing, like bosses, like the bosses they are. Nine volts. Andrew Black say 9. A man say, somebody say 2,311 volts. That's an interesting number. A man say go and sleep on it. A lot of people holding on the, sir, I tired now, I feel like one day. Yeah, but injustice holding on. You go through, you wait through all the easy thing, and I'm now going into the killers now, the logic gates, the motor and the generator, and you have to go now by. I feel by the time I finish, I might have 100 viewers. I'm going down strong. Me and them 100 going down strong. When the chat does sleep, 11 volts, everybody getting 11 volts. Everybody getting 11 volts. Alright, so we'll work it out and see where we get. So obviously, in physics, you work out one thing to get the next thing. The V, to get V, you need V equal IR. So you start off with what you want. I want V. And you check where you have and where you don't have. I have I, as look at here, but I don't have R. I only have all these things. I need to get the total R, which is what we are doing all the time. So what you'll do is be like the total would be the sum. You understand? The parallel thing now. Parallel. And you add 1/2. We're going on with Chavi there, Lubia. 1/2 plus 1/3. 5, 6. 6/5 is the parallel. So the total is going to be 6/5 plus dB dabba 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 1. Is use product of sum for total resistance. Yeah, you can use that by teaching that from here. Especially I next thing to put 3 resistance in parallel and thing. I want to hurt people head with that. Right? But I see you. If you're comfortable with that, like some people use product over sum, if you're comfortable with that, free up. Great is the Cohen and he shall prevail. Right? So let's keep going. So this is 2 1/5. And then now we could go to V equal IR. Where V is equal to I 5 times 2 1/5. 2.2. Excuse me, and everybody get 11 volts. Okay, change of the question. What if this wasn't given? And what if, let's say that's a variable resistor, This could be as hard as it comes. This is why I say it's better to understand than to memorize of questions in physics, because physics could come anyway. All the ways is easy if you understand. If you don't understand, it can come in millions of different ways, right? What if they say this is a variable resistor and they want to figure out Rx, given that V, the voltage, is equal to 20. It's 20 kind of high, boy. Okay, let me make 20 volts. I don't know why we're doing a 20. Okay, let me make it 9 volts. Sorry to stop those working. 9 volts. So given that the voltage in the whole circuit is 9 volts, some weird comments here, man, that the whole circuit is 9 volts, what is Rx? What is the resistance there? How are you going to do that? How are you going to do that now, guys? Let's focus. Kicks, you're this close, you're this close. To getting a timeout, brother, man. This close. This close. Please don't make me do what I have to do. You know I don't like to give people time. Whoa, Ryan says 0.6 already. Joel pull out 0.6 already. Some killers out here, boy. Cool when you're salting on the wing. 0.6, Addy pull it out already. Yeah, man. Matthew thing 0.6. Or you could put in a little ohms too. Make it good. Thank you, Kicks. Thank you. 0.6, 0.6. Alright. So the working fate is like this, right? V equal IR. So R will be equal to I over V. You figure out what the resistance is that we need. Like, if we don't know nothing before now, remember we're looking for the resistance, eh? This will be the total resistance here. So this total resistance for the whole circuit must be equal to 1 over the voltage, not 1 over the voltage, I over the voltage, which is 5 over 9. So it's 5 nines we're looking at. So this means you find the resistance in parallel, which turned out to be 6 over 5. You catch track going, you catch track going, brother. Catch track going. This is the resistance in parallel. That wouldn't change. We didn't change anything there. But RT must be 5 ninths. So RT must be equal. RT is 5 ninths. So 5 ninths must be equal to. Okay, this is impossible. 5 V is equal to IR. R is equal to, my bad, R is equal to V and I. R is equal to V and I, 9 over 5. Anybody correct me? Do some power here. Nobody correct me. R is equal to V and I, 9 over 5. So 9 over 5 is the total resistance. 9 over 5 is the total resistance, which is the resistance in the parallel plus the resistance which we're trying to find, Rx. So from that we could see Rx must be the remaining 3 over 5, 0.6 ohms. Well done to those who got it out very quickly. I can't see you working at the moment, so I could have corrected you. 1.8, not CNC, not CNC, nobody can see behind your video. What? Oh. That sucks. That's not it. Let me turn on the editor. Me, goodbye. Oh, they wasn't seeing this. Right. So that's why I can correct me. Well, good. Do you think this is ring? We all make mistakes. Easy. Alright, yeah, so I made the mistake I make was when I was looking at R, I just for some reason I put I over V. It should be V over I, right? So this is 9/5. So this is the total resistance here. Once you find the total resistance that the circuit needs, you just say that the total resistance, and this is a lovely question for them to bring. If they bring this on Monday, I would be laughing. you just say RT is equal to, this is the resistance in parallel plus the resistance we're trying to find. And yeah, use your algebraical skills. Why is in the chat? Let's move, man. Let's move. I'm gonna come back alive here. Can you all tell me the definition of a few things? Now there's a whole fuse and earth question that went along. So we having difficulties. Fuse and earth. Know the definition of those. Know what kind of rating fuse you can choose. For example, if you have if you have a 4 amps running here, this fuse, you can put a 3 amp fuse, right? It can blow. You're looking at a 5 amp fuse, maybe 6. Fuse prevents sting, bap, bap, bap. Fuse breaks the circuit in case of high voltage, bap, bap, bap. I keep drawing behind me. Now, this question came recently and I do it out already. The earth is flat. Ministry of Works. Ministry of Works and Transport. I need some conduct, please. Ministry of Education, I don't know. You tell me. The earth and... Okay. Right, so it uses an electrical component to protect the circuit from excess current. Yeah. The fuse is not a circuit breaker. A circuit breaker uses a mechanical. So your circuit can break and then you can turn back on your breaker. Right? But a fuse is actually burn out. You can turn back on your fuse, it burn out. SpaceX about to launch a rocket. That's cool, but teaching the Caribbean better is of more importance to me. So 200 people, hopefully we could keep it to over 100 by midnight before we finish, right? Okay, so we have the definition of a fuse there. Earthing, or earth wire, provides, what's the definition of earth? So we have this. What's the definition of the earth? Somebody say no, sir, when you're looking like you need 2 burners, you need to wake up. So you're looking very tired. Really? I do find her looking tired. My fuses. You're looking more important because these children. No. Stop it. I will start to ban people that are pushing my kindness. Right, so the breakers, you know, if a breaker break, you can pay back on, it's mechanical, you know. But the fuse burn out, that's the end of that. You need new fuse. And that's about it with the fuse. You need to know your little problems with electrical hazards. You all can check back the video I do on that. I don't need to talk about it too much. Press some likes on the video. Good reminder, Ryan, but we'll press likes on the video. Let's move forward. Moving forward. So you have your mains, you go to your circuit box, the fuse box, you go to your distribution, and you go to your different appliances. House wiring. Everybody should know the house wiring works. But everything is connected to the ground. You have the live wire, you have the neutral wire. Maybe I should just draw a little heads up on that. So you have your mains, M for mains. You have your fuse box. Wait now, my iPad wasn't charging all that time. My battery dying here, right? Alright, so I'm going to take out the laptop charger and turn on this one. We had a share chargers here, boys. Right. So you have your main. What do you last talk about? You have your main. Woo! You have the fuse box. This is going to whatever you're using to distribute. And then there's going to your appliances. This partner readiness. Distribution. Right? But what I'm saying is this top wire, I could call like a live wire. You should have a neutral wire running. Let me put the ground again. Right, so here. When you're going to your distributions, You have a ground wire as well. So if they ask about this, you know to label this. Hey, I went behind myself again. So you have your ground. This is the symbol for ground. That kind of thing, and 2 strokes. I don't know why I put 3. So you have your ground. So check your IG. I can't check my IG right now, but the time I take to check the IG, I think my energy will just drain out on that. Right. So this is your live. This is your neutral. So if you they would ask that though they'll ask you to draw, but they could ask you to label. This is your ground. You have your main box, your fuse box, your distribution, whatever. And this is like your appliances, like maybe fridge, right? Refrigerator. Why is in the chat? Go take a nap and get back to us tomorrow. No. It was very tempting when you tell me there, but I need to get this done now because you know what's gonna happen tomorrow. Alright, so diodes. What's a diode? What's a diode? What is a diode? And what is half wave rectification? Once again, this question came recently. I try my best to write that day. Big up, Prezi, big up. So we're taking a break. We can't take a break. If we take a break, people will knock off. We're going straight. We're nearly done earlier. Okay, we're not nearly done. We have about an hour and a half. This is time. Yeah, we're finishing 11:30. So what book you using? I'm using real books. I use any physics book good. So the definitions flowing in. Diode allows current to flow in one direction only. So I'll speed it up a little bit. Definitions, and I can just pull it off your book. So a diode electrical component which changes AC to DC. Yeah, something which regulates the flow of current. Nah, that too vague. That one too vague. After rectification is a good converts it AC to DC using one diode. Okay. So let's draw the little circuit that will cause halfway rectification so we catch an idea of what's happening. This is just a load. This is a triangle and a line like this. So this symbol here means AC supply. The current is going like this and then it's going like this for over at a hertz, at a frequency. So it's going one way, then it's going one way, then it's going one way, then it's going one way. When it go like this, it's accepted. So remember the supply would be looking like this, right? Sinusoidal. But what we're going to notice here is that only when the current is going through, we get in it. When the current is going forward, we get in it. This part here is getting rejected by the diode because the diode only allows current to flow in one direction. And that's basically it. So this here is a half-wave rectification. This is half-wave rectification, and this is AC current. Why is in the chat? And an example of direct current would be like that, right? By the way, the units of voltage and time, or current and time, anything. Alright, so we into logic gates. Type of logic gates. What type of logic gate is this? What does it do? What about this one? So that's the first one. What about this one? And this one. So that's the third one. And the two specialty boys. So everybody's seeing them there. Need to know how to draw them, need to know how to do the map. the little truth table of them. Let's get these truth tables down. So the NOT gate flips the input. We normally label each thing. We does label each thing now, boy. Yeah. So if I put this X and Z, my input would be X, my output would be Z. And if I was 1, it goes to 0. If I'm 0, I go to 1. So the NOT gate flips. What is the word by? It inverts, right? It inverts. So the NOT gate, if you are 1, then you become 0. If you are 0, then you become 1. Normally we start off with 0 and we write in a truth table. Let's look at the next one. Let's look at the AND gate. So you make this X and Y and then Z. So we have two inputs now. We have X, Y. So this is just the basics. We'll do some questions just now. Z. So what I do is put 0, 0, 1, 1, and then 0, 1, 0, 1. Like that. Right? And in this case, I could probably come across here. So, yeah. So what's the output going to be? Well, this is an AND gate. It means both inputs must be positive. Both inputs must be there, giving off current, whatever, for an output to happen. 1. Everything else, negative. Everything else is not there. So, only this one is accepted. Well, how do we say this? Okay. And the NOR gate, so get back to me with this when I get a rest. Woo, people dying. The input, now if this was before exam, the remand jack still here. Y output Z, in fact, is just increase. So 0, 0, 1, 1, 0, 1, 0, 1. Anybody, once it have a 1 in the dance, you will get an output, right? Yeah, people leave into Netflix and chill, or just to chill. I feeling the need for sleep creeping up. So yeah, both and X are both high. When my die hard say they had to go and sleep, I know things rough. Obviously, if people had to go and sleep, go and sleep. So the NAND is like if you stick a NOT gate at the end of a AND. So all of a sudden, the NAND will change like that and that like that. You understand what I'm saying? The NAND is like if you stick a NOT gate at the end of the AND gate. So I am lost. Stop saying you're lost. Triggered. Stop saying you're lost. Say what is the problem. When you say lost, what am I supposed to do? We need sleep. I sleep when I reach home from school. I get or gate, right? So where lost? Where lost from? What you don't understand? What you don't understand? You need to pinpoint what you don't understand. Otherwise, I can't help you. NAND gate is multiply X and Y and invert. Yeah, whatever floats your boat. Whatever floats your boat. The best way to remember the NAND gate. Yes, you are damaging your health when you don't get a proper rest, which is what I'm doing right now. But I will recover. I'll recover. This may be the last time I'm doing this like this. Alright, so 1, 1, 1, 0. Right, so that's a NAND gate. I don't like to think of the NAND gate as not an AND, although NAND it makes sense. I like to think of it as and then you put a NOT. Somebody say everything. can't help you when you say everything. Okay, so the NAND gate is like you put a NOT gate behind the AND gate, right? Somebody said we're working from the energy sum. That's way back in quite. I don't even remember the working from the energy sum. Okay, let's do a question on this. Best way to see it is a question. Zip zap, zip zap, zip zap, zoop. Now, probably my favorite part of physics in CXC was these, because it kind of fun just to work all these things, right? It's like a cool down. To map all these things will be kind of fun. I know it's a weird thing to say. Why? So what's the question? Draw the truth table. Right. Draw truth table. So it'll have a few truth tables to draw, but in the end, the truth table they really want is basically this: X, Y, and what's the N? Z. I missed out some letters. P and Q. So you don't say you lost. See what is bothering you. Give us location which you are missing so we can locate you and help you back. Yes, that's what we should be doing. So Z is missing. Thank you. Thank you. So Z here. I just can't remember the gates by looking at the drawings. What is there not to remember? It's only three things: and, or, and not. That is it. That's it. Three things to remember. I'm gonna go back in the corner. Go back in the corner. I'm so lost, I don't even know where I'm lost. So not everyone like you. I understand that. I understand that, believe me. All those talking about this easy, this simple, not everyone get it like you. I understand that. I understand that. But this is common sense. I think Ziana is trolling us. Trolling. The man say he detecting trolling. Last time I thought somebody was trolling, there wasn't trolling there. So yeah, we drawing a little diagram here. Z. This is what they want at the end of the day. They want you to fill out this truth table. So those who understand it, kill it off. Doing all kind of things. I doing the most. Come across here so now, buddy. Well, apparently that part of the bit book right. You're blocking again. So this is what they want. Yeah, no one's blocking. Alright, so when we do all this question, hopefully some people who lost will kind of see a little logic taking place here, right? So let's do all the questions. So we need X and Y. You don't really need X and Y. You make up your own X and Y. Okay, let me put it in 0, 0, 0, 1, 1, 1, 0, 1. That's how I want the X and Y to work. Free up all yourself there now. So you need to figure out Z. So what to do after CXC? The first thing you need to do after CXC is make money. You need to watch yourself in the mirror and say, not enough money making. I'm serious though. I tell my students that. Go and figure out a way to make money. I can give you my WhatsApp. My parents deleted my IG. I know what to say about that. I can't communicate with everybody at the same time. Imagine if I communicate with just how much I have in here, 198. I don't have enough time. That's why I do this. Good question right there. As you can see a number, but I may not be able to add it, right? I'm very sorry. So you leave all the inputs. No, look the inputs right there. Look the X and Y right there. Anybody put answers yet? This person pointing. Oh, Z is 1011. 1011. Was that what I got? 1011. Yes, that is correct. Shamal, whatever. Shana. I woke at Shana, right? Sorry if I pronounce it wrong. Loic, I saw your answers, bro. It's correct. Ziana, I saw your number. I didn't have time to add it right now. You could probably figure out my email. CohenSpringerTT@gmail.com, and you can email me, right? 1011. I have answers. Okay, it's Luke's. Luke. What a spelling, my friend. Alright, so Luke, how does radioactive decay? Oh, we're doing that tonight. Okay, let's go on with, so people want to see the answer. How you get Y? How you get Y? Y was given. Those are the inputs. Those are given to you. X and Y were given. Shana. Right. Adi, Shana, Daniel. So I see real people getting all answers now. All the usual answers, boss. Getting it out. The first thing though, you need to map P and you need to map out Q. You need to get the truth table for P and Q. P and Q, right? So we can work with that. By the way, PQ, ting. So let's draw the truth table for P. I need a line in my life. So we're watching P. We see in P coming from what type of gate this is. This is an AND gate. This splitting up here, this is the Y. So this is really Y. And this is X. So we have our X and Y as the inputs here. And we're trying to figure out what P is. So you use the inputs given. 0, 0, 1, 1, 0, 1, 0, 1. And if it's an AND gate, that's the AND gate. Both of them must be present, right? So good, we have the input for P. Put that in my back pocket. Now we need the input for Q. So looking at Q, we'll see that Q just has one input because it's a NOT gate. And the Y here, well, we just use the Y inputs that was given here to work out what Q is. So let's draw that. Once you give up your field. Hey, that people's just dropping truth bombs in the chat here, boy. Truth bombs. So Y, Q. One of the things as a teacher is how to understand where a person losing out and then help them. So that is why good teachers, it's be hard to get good teachers. Some teachers good at explaining, some teachers not good at figuring out where you losing yourself. To teach is a real skill. And that's why you need to help your teacher sometimes. So remember the input for Y was given. 0, 1, 0, 1. We have to put it in that order so that we don't mess up when we just pulling out the answer. 0, 1, 0, 1, right? 0, 1, 0, 1. And it's a NOT gate. So all of a sudden Q is going to be 1, 0, 1, 0. Because the NOT gate is flipping it. Right? So that's the input thing. This one here was a AND. This one here was a NOT. I should have put the AND a little more to the side there. Right? So what do we have? We know P, we know Q. Now just to find Z, because P and Q going in there to make Z. So one more table and we done. One more table and we done. What kind of gate this is though? OR. There's an OR gate. OR gate. So whap, whap, whap. We put P here, we put Q here. You know, P is actually 3 zeros and a 1, and Q is actually, you see Q over here? Q is actually 1, 0, 1, 0. So the OR gate forces and thermal physics coming in for claw graph. Also reactivity with Einstein equation coming. Alright, Luke, if you say so. Hey, I'm blocking. Thanks for writing that day. I saw a custom being in the next corner. I draw that day. Sorry about that, people. I'm going to replace. I'm going to rewrite it. So P, I got the input for P. I got the input for Q. And I put it here in my truth table. And the answer now has to be dictated by an OR gate. So OR means once I see 1, put 1. This has a 0, so I have to put 0. 1, 1, right? And this is the answer for Z. I can safely take this answer just so, whole as it is, and put it here now because I kept everything in order. 1, 0, 1, 1, that's the answer. Why is in the chat? I need the green screen. Look at doing it again. Yeah, I had the green screen before, but my lighting, I had another light and a green screen borrowed from somebody and I gave it back to them. So, you know, pressure. Why is in the chat? You need proper lighting for your green screen. Right now, you have my ring light. So, pressure. Can we move on? Yeah, let's move on. Y'all want another one? I'm not doing Newton's laws today. Definitely not doing Newton's laws today. Coming from someone who came out of depression only October last year, where I was even hospitalized, right, and put into a mental state to where I am now. It says a lot, I do not give up no matter what. I think that truth table for the all thing, then your book has concise revision, of course, is really helpful, right? Can you do kinematics? So all them Newton business and thing, another day. You have to try your logic gate questions, try some more logic gate questions. I'll do a live tomorrow, but I don't know if I'm not live tomorrow if I'm doing IT or integrated science. So I still have the whole of magnetism to do, but it's kind of like I run out of juice there. But that would take me like about 1 or 2 hours to do, between 1 and 2 hours to do. We did all of the electricity. That's all of electricity and logic gates there. Alright. Let me see some Y's in the chat if you could go on. Let me see some N's in the chat if you're ready to call it at night. If you could do that magnetism tomorrow before I do IT or integrated science. Why is in the chat for? If we're going on or like we're going on? People out here. People ready out here. So if all ready, I'm ready. So let's talk about magnets. I'm going to skip out the whole of magnets because I honestly find that really easy. I'll just mention some key points. I'm not skipping out magnetism, I'm just skipping out the little basic part in magnets here. So some key points. Magnets exist either attraction or repulsive force. Like forces attract. Sorry, like forces repel. Like this happy hour, but happy hour things that start happening. Different forces attract. I don't drink coffee. Different forces attract, right? A free release, if you hang a magnet like this, and it's suspended freely, it will align itself with geometrical north and south. Geometrical north and south, right? So the two ends of the magnet is like north pole and the south pole. The closer magnets get to each other, the stronger the forces of attraction will be. Closer magnets get to each other, the stronger the forces of attraction is going to be. Non-magnetic materials can get, obviously, there are different degrees of magnets. There's permanent magnets and temporary magnets. What is a temporary definition for temporary magnets, definition for permanent magnet. I already do circuits. Why she asking me to do circuits though? But I already do circuits. I did circuits with the circuits is when you have this coolness making my nose thing. The circuits is when we have the resistors and thing. Magnets get attracted to each other by magnetic induction. So we see the definition for temporary and the definition for permanent by kicks. Permanent magnets when kicks, that's not the definition. Bayesian King have the definition. That's the definition for temporary. Oh, well done, kicks. Well done, kicks. This thing messing up the nose. Alright, what else, boy? What else? How can you plot the magnetic field around a magnet? How will you plot the magnetic field around a magnet? So like say you have north and south. What can we use to plot the magnetic field around a magnet? Yes, it's going to go out the north and into the south. We know that. But what do we use? We could use the compass method. Very good, Josiah. It has some people who just jump out and see the correct thing and just go back into hiding for a whole lot. Right, so you can use the compass method. I'm going to draw this any meter. I really not enthused to draw this any meter than this actually. So I just draw it shortcut. I just draw two lines. Like that. So you're going out the north. That's very important to remember, especially when you start to go into solenoids and generator, Fleming's left and right hand grip and them kind of thing. Out the north into the south. One more thing, what is a neutral point? The compass method is where you take a compass and put it on everything. So you're taking small compasses and placing them and they'll go along the magnetic field and they just draw along there. Remember the compass will point towards the south. So Luke said what the definition of a neutral point is. A point where you have no magnetic field. A point where no magnetic field is acting, and that happens when you have two bar magnets like this. And they have the same. And boom, in the middle there, you call that the neutral point. You understand what I'm saying? I might leave any not. So if you put anything here, it wouldn't move. Neutral point. It's like almost like they cancel out each other. Alright. So that's the basics then. Now we could go into thing that actually troubles people. That's what I want to make sure I can answer everything here. Must not to sketch your magnetic fields. Remember out the north into the south once you know that you're safe. Right, so we're sketching electromagnetic fields now. Electromagnetic fields. So what are the electromagnetic fields you need to know to chat? You need to know to sketch. Yeah, but happy or rich. What are the electric fields we need to know to sketch, people? CSEC mentioned you in their story. Alright, CSEC. I don't see no answers though. We need to know how to sketch. I've seen people die instead. The solenoid. I'll just talk about the solenoid. That's kind of yucky. Maybe I need to use a bigger thing. Right, so that's a solenoid. Remember, our current is flowing here. Into and out of. There's just one thing I kind of learned how to do with a solenoid. Can't see. Current going into and out of the paper, yes. So like you have current going into the paper, current coming out of the paper. What else? I think that's it. Straight conductor. So like if current is going up here, what's the field? Straight conductor. So you're gonna do all of these, you're gonna do all of these. You're gonna do all of these, and I feel I want to call it George here. So I feel that pain in my chest and feeling like I'm getting useless here. Alright, so let's do these. So what I remember with this solenoid from ever since back whenever, you need to watch which direction the current is going. Now with these electromagnetic fields, what's happening is that current passing through some wire and it's creating a magnetic field around the current carrying conductor. Around a current carrying conductor too, yeah. So that's what I have, the current carrying conductor. This is a field, a thing going up here. So like this one is the easiest one to do. Because with this one you use your right hand grip. Right hand grip. Right? So there's the right hand grip, there's the left hand rule, and then there's the right hand rule. Fleming's, right? The left is for motor, the right is for generator. The right hand grip is for just fields. So you need to get that down. The right hand grip is the first one you'll see in your book, the first one you'll come across. Right hand grip. That's no left hand grip really. You deal with the right hand grip. And the left hand rule with Fleming's is the second one you'll see. That's when you start to deal with motors. Most book, this will be the second one you'll see. That's when you're dealing with motors. The right hand rule is for generators. That is when you're taking, that's when you're doing the opposite thing now, you're creating the current. The left hand rule is when you're taking the current to make motion. This one is when you're taking motion of a magnet to make current. Okay, so let's go back. Let's come back into joining electric fields. So right hand grip means you hold on to that thing over there, and then you'll easily see that your fields going like this. See the next thing in the book, but okay. So which direction should it go? Should I put it this way, or should I put it on this side? This way. Right or left? Yeah, Maxwell's screw rules, so I don't really deal up in the Maxwell way. The right hand grip just confused me. Somebody saying left, somebody saying right. So our next person say left, our next person say right. What's really going on here? Which arrows are correct? Are these arrows correct? Or these arrows? The right arrows or the left arrows? It's the right arrows. Right hand grip. Where are my fingers curling? In this kind of way. So these arrows following that curl. Like this. So the right hand grip, you have to watch which way your finger curling and your thumb running along the where the current is going. This is conventional current, by the way. So, in other words, I can't put arrows like that. They have to put arrows going this way too. So, whoop, like that. That's the right hand grip, right? So flip your screen. No, I don't need to flip my screen. I think I could do. Oh, the video like a mirror. Let me check and see if what I talking about makes sense. So I'm loading up the live video here. But like I don't want to load. Right. My camera reverse. Oh crap. Well, that sucks. I can flip my screen, yeah? I can flip this screen, but I can't really flip this screen. Let's flip it. Flip the screen now. Tell me if this makes sense. I mean, I flip this screen. That's important for when I'm teaching. That's really important for when I'm teaching generators. And things, but always flip this again, flip horizontal. But everybody get it though. It's alright, we get it. I seen that. It's the right hand grip. So if I say right hand grip now. Come on, catch back up with me there. Let's say right hand grip. Right, it works now. It ended working it? Yeah, right, it working it. So right hand grip. So going wrong like this. Yeah, we get it. So that's good. So the right hand grip. So that while you're probably just watching me like, what the heck? So the right hand grip looks like this. So the way your fingers coiling tells the direction of the tool. I still kind of confused with the grip aligns to the paper. How the grip aligns, you have to watch your finger. So it's like my hand is the wire. My hand is the wire going up so. And I use the right hand grip where my thumb going in the direction. And the way my fingers curl telling you which direction to draw. And if you're watching the diagram, that's the direction to draw. Imagine gripping the wire with your hand. Right. Okay. Luke, Luke, message me in my inbox. I find you have some nice predictions there. Alright. And a few people is like a whole, I see a man with a whole wall, a whole big thing, and he crossing all different things and he predicting you're coming for chem. And they send me, and some of them students sound good. They're predicting pretty good by crossing all different years and things like that. What? And they could go into some kind of statistical analysis job. Anyhow, so that's that. That's the right hand grip. We spend enough time on that. So this is how the field looks. This is how the field looks in a current carrying conductor. By the way, if the current carrying conductor was going down like this, then obviously you draw the same circles, but the direction would be the next way, right? Because when you grip it going down now, it will curl this way, right? I'm predicting Hooke's law for the thing. Alright, what about in the paper and out the paper? You're using the same thing for this again. Which one of these symbols means in and which one of these symbols mean out? Which one of these symbols mean in and which one of these symbols mean out? So somebody say shooting an arrow. The X is in, nice. And this circle, that thing is out. So X is in, right? So just going in the paper, hit them the right hand grip like this. So we're going in the paper, you're expecting to see. Well, I wouldn't send out the answer. Let's draw some circles here too. So is this correct? I'm going to put both of them in the same direction. Which one correct, which one wrong? Which one is correct, the left or the right? Which one is correct and which one is wrong? Nice. What? Which one is correct and which one is wrong? I seen the top people getting different answers each. Let's get some consensus here, grinders. This is the 188 left. The last of the Mohicans, the killers, the people who could go down, who could real grind. Let's pull out some consensus here. So some people saying the X is wrong, and some people saying the O is wrong. Well, let's check it out. The X is going into the paper, into the paper, into the paper, right? So I'm actually putting my thumb on it. See my thumb making that squiggle thing there? That's my thumb doing that, right? And now, this is going to turn like this. Like this, right? Turn, turn. No, I don't know how to fix this thing back. I should have never touched it. Right. So, because it's turning like that, that one is actually wrong. So I'm going like this, it's turning like this. I just need to follow the directions of my fingers. Bam, bam. So, dip, dip. Right, so everybody good? And now the O is going out of the paper. So this is curling like this. So I just need to follow the directions of the curl of my hand. Y is in the chat. Y is in the chat. Curry goat and bus up shot. Next. Right? So I know this helping a good few people out of this 190 something people. Hopefully we getting some good work done here. Feel we will cut this here. Normally I only go for 3 hours at a time. It's kinda running up 0 to 4 hours here. It's a pull, it's a pull. Now how are we gonna do this one? How are we gonna do this one? Now people say you can use the right hand grip for this too. There's a way to use the right hand grip for this. But I find it kinda tie up now. So the best thing I'm gonna tell you the method I use for this. See what I do here. I'm going to tell you the method that I use for this, and hopefully it helps somebody out here. Hopefully. I think of this. I'm just inserting a new slide. You see this part here? Think of this part here like, pay attention, eh? Like that. That's the first ring, right? That's this. That's our first ring. The current is going up in this example. It could be going down up, right? So it's going up. There's 2 things I learned. I learned the north. Anybody else learn it like this? And I learned the south. This is how I learn it. Anybody else learned it like that? So I'm going to learn the North Pole and the South Pole, and then I'm going to show you why. And to me, this is like, because sometimes in the solenoid, they had to label the North Pole and the South Pole, so I might as well just learn it like this, you understand? So since the current going up, the only one that fit in here, North wouldn't fit here because watch, the North not fit in here. This is telling me that the current going anti-clockwise, not saying that the current had to go anti-clockwise, but the current actually going clockwise. That's where the current going. So what really fit in here? South pole. So this means this is the south. That's the south pole. And if I watch it from there, that's the south pole. That means this had to be the north pole. Now what you know about south pole and north pole? What you know about south pole and north pole? The current is leave which side? Which pole will the current leave? Which pole will the current leave? Current always leaves, or the field, or what the magnetic field will always leave the north. So it will be going through like this, busting out the north and coming back like this. So let me get a diagram from the internet. Solenoid Solenoid. Let me see some wise if you kind of understand that. Somebody say cool when I reach Leron. Hi. 3 hours and 41 minutes past. Right. I'm looking for what? I'm looking for a solenoid. You see when I get this late, I start to get not good. I teaching whole day in school. Went and fix some programs, so not program, just fix up something. What am I looking for? A solenoid, electromagnetic field. Diagram, so I could explain again. Once again, I can explain. Do some nice explanation. Whew, some of these diagrams real extra, boy. It's a bit too extra for me. So I think this is like the last thing we're doing for the night. So just hang on, just hang on. I'll save the generator for next class. Generator and motor. So here we have a solenoid. It's a little different. It's a little different. I don't know why I press. Might come off. Why I press, right? So once you figure out that method, to me, you're safe. You're safe. Yeah, going live tomorrow for sure. Okay, let's see how we'll use it in this. Now, your spatial understanding need to be good. You need to be able to see things on paper and kind of visualize it three-dimensionally. And I understand that there's a percentage of people that's just very hard to do. It's basically how you grew up, what you was exposed to when you was growing up, Legos and them kind of thing, and how much of that you get exposed to, right? So there's this going like that. Now you see it going down and it going across like this. So if I was watching from this side, this is what I would see. If I'm watching from this side, right? This is what I would see. I would see something coming down like this, and turning like this and going back into the paper. So now I could use my north or south pole test because the current is this going down like that. Remember the north says that the current has to go clockwise. Sorry, anti-clockwise. The north pole says that the current has to go anti-clockwise. But this current is actually going clockwise. It means that this is north. This is actually south. And when I put my arrows on the edge of the south, bam, it's working, man, it's working. It's following the pattern, right? So this means that this here is the south pole, and if you watch, they label it as the south pole as well. And this here is the north pole. Well, obviously, if you find the south pole, you find the north pole. And the electromagnetic field will, or to draw the field now is easy. It will leave the north and enter the south. It leaves the positive, enters the negative. It leaves the north, enters the south. Why is in the chat? That's solenoid for you there. Now there's a way to do this with the right hand grip too. I'm not going to go into that, but if that could float you. Right hand grip? Okay, let me explain it using the right hand grip then. With the right hand grip, you're following, but keep in mind, even if you have the right hand grip, you still need to know how to label the north pole and the south pole. But let me explain the right hand grip. With the right hand grip, you're following the curl and the solenoid. So this solenoid curling like this. You're following the curl and the solenoid, and your thumb will point in the direction of the current. That's it. So your hand need to follow the curl of the solenoid, the curl that points in the direction of how the current is going, and your thumb will point in the direction of the electromagnetic field. Right? So the right hand grip, if that floats in your boat, free up yourself. And if you want to use the right hand grip to try and figure out which pole now, remember after you figure out the electromagnetic field, which direction it's going in, curling the wrong way? No, I'm not. I don't know if you're seeing something wrong. Not curling the wrong way. I am not curling the wrong way. And I curl like under so. Because it come down and go forward like this, right? So it come down and go forward like this. It come down and go forward like this. And going so. Alright? Yeah. So we feel going so. Well, I actually pointing in direction that thing pointing in here, but when I do so now it pointing so in the you understand what I mean? How the camera flip, that is what happening. I pointing in the correct way, trust me. How to show this boy? This inversion thing is real messy up when you have to do these kind of things. Face the wall. Thanks, Luke. Thanks, my brother. So curl underneath. I just retarded by this Wisconsin. We're curling like this. No, they're not helping me. They're not helping me. Forget it. Forget it. Forget it. All you understand, everybody understand. With the right hand grip, you use the the fingers represents where it's curling, where the how the solenoid is curling, and the thumb represents the direction of the field. It was a good night. It was a good night. I wanted to I couldn't finish what I wanted to finish. I have like about what 10 more pages to go, or less 5 to 10 more pages to go, which is basically motors and generators. So that'll be a separate video by itself. That might take me 1.5 hours. That'll be a separate video by itself. Tomorrow I'll start off really with that. We went from about 350 people to 200, which is not bad. Normally it's dropped down to hundreds and in the 100 and thing. Alright. So I'll do that magnetism thing tomorrow, then I'll do waves, optics, then I don't know if I'll have time to do anything else. I may have time to do the first part of chemistry, maybe I could do heat and gas laws and things. Maybe I could do those kind of things. That would be the night before the exam. That would be the killer session that everybody's be inside. And in between all of that, I need to get time to do some IT, hopefully. I can do some programming. And I need to get, I think the hair green back, of course. Of course. I need to get time to do some integrated science. So some infotech and some integrated science. Hopefully I get time to do that, some of that. Well, you see what's going on, right? I have to balance sleep, I have to balance work, I have to balance time with my kids, I have to do help my son do his homework, I have lots of things. Plus I'm a health. And as young as I used to be, so I can't be going without sleep for too long periods because that can damage my organs. Anyway, blessings. We will be doing multiple choice, geo, chem, physics, bio, add maths, multiple choice. Hold it down. Can the thumb show the note? Yes. Thumb points to the note. Thumb will point to the note. You're using the thumb to point to the note. So the thumb will show the electromagnetic field. So it's going to point to the note and out. Right? I always make appointments with my barber that I was in a hurry. Like I always call Lily and he tell me, yeah, come through this time and thing. I have my barber set up and it's just a pure bad day that caused this hairline thing to happen. Hold it down. You're welcome to all the people who saying thanks and thing. This was a nice 3 hours and 15 minutes. If you haven't followed me on Instagram yet, follow me on Instagram. Now my Instagram look wet. And also I do surveys on Instagram. I figure out what people want to do and I post encouraging stuff and If you're off of Instagram now for exam time, it's okay. It's okay. Don't go on Instagram just to follow me when you're, because Instagram could be extremely distracting to students. When you come back on, we can link up. Blessings. I have real good ideas and things for what I'm going to do after exam season. For those of you all who don't know, a lot of you all who do in physics here will probably do pure maths in Upper 6. I am going to have an online pure maths course. It's going to be 200 a month, 200 TT a month. If you're interested in that, the registration for that will start in 2 weeks. There are already people registering for the maths course, which is going to start in about a week or 2. But the registration for the pure maths class starts in July. So we have time for that. If you're going to do pure maths and you want to work along with me in like a class like this every week for 2 hours, and then it'll be in a WhatsApp group. I feel like that's be almost as important as the live, because right now I have a WhatsApp group with, and I'm sure some of them may be here, a WhatsApp group that I did for the advanced crash course, and I didn't delete the group. I left it open, and wow, that group was very, very helpful for the students there to get past papers, notes, pass along this, send information, ask questions, get help from each other. So that'll be really nice for pure math students when the math start to get a little harder and you have to figure out stuff. If you're working along with me in that, you will be exposed to that group. You'll be able to converse with each other there. So it's a good idea. So look out for when the registration starts. When the registration starts in 2 weeks or so, I just need to make sure I have everything organized. I also need to fully polish up on my pure maths because I haven't taught, I didn't teach pure maths this year. I just teach one kind of way, right? And I used to teach pure maths privately all the time. So I just need to polish up on the syllabus and make sure everything running smooth and make sure everything is well prepared. I see people going, so goodbye, see you teaching Cape. I teach in Cape long time. Fully polish up the forehead. And XSS gaming, you just come out. So how you find ADMAT's exam was? I find it was really nice. There's only one tough question, the stationary points question. What time tomorrow, sir? About 6 o'clock, 5, 6. Economics is science. I don't teach economics or business. I don't drink Red Bull. Yeah. All those things coming. I'll have a nice stationary. Yeah, that stationary points question was a killer. But I write the answers for some people on Instagram already. All nighter, Nana do not all nighters. Just so. I need to live. I need to live, people. Living is nice too, you know. Living is feel good too. So where's the class? What class is an online class? So the class is in your bedroom, the class is in your study room, the class is at your table, the class is wherever you want it to be. The class can be in Starbucks. Wherever you want it to be, the class will be, because the class will be running from your phone, from your iPad, from your laptop. You'll be getting a private invitation to the class. Bye, sir, thanks so much. Bye, businesses be. Think, bap, think, people typing what's the madness. What time tomorrow for physics? Maybe about 6 o'clock. Online classes for real January maths. If you're interested in your online classes for January maths, this is the number to call for January. If you're interested for maths, let's give this number very quickly. Ado 790-8813. This will be the number to register for the pure maths as well, so you can probably take it down, but don't call it yet for the pure maths because the pure maths hasn't opened up registration. Right? Any other questions? I never went to Starbucks thing. Multiple choice for real though. Yeah, the multiple choice pump coming right after done physics and them thing. So when is infotech, I don't know. Will you do a prediction for the topics in CSEC? I don't know. Tomorrow 6 p.m. we out day passing winners and making a people. Much love, my brother. So you're not tired? I am tired. Do we have to reset maths? Unsure about that. Unconfirmed. I find CXC notoriously quiet with this boy. Just why send out an update on hearing rumors that this one say that, this one say this. People inside CXC saying this one. Send out an update. So follow me back on IG. Okay, send me a message and tell me to follow you back. If your profile is edifying to me, I'll follow you back. Like, if you assume substance that, because I don't have a profile like it distract me to be on my IG. So that's what your profile must be. It must be uplifting and uplifting someone. Some way or the other, whether it's entertainment, whether it's just fun, even if that is uplifting. But if your profile is depressing. Alright, later. Go and stay and teach us about life. We're going to be learning about life when we do an exam in the next 2-3 days, right? I'll be teaching you about life when we do have stuff like that, conduction, somebody living in the past. My profile just have my parrot. Go and sleep. We gone. Hold it down and live. We can stay here and hold talk forever, but it's time to roll out. See how sweet the talk is that when it's time to roll out. Later, president stream there. Don't forget to press like. Don't forget to go on my Instagram, follow me, message me anything, blaps. Later.